Hello there and welcome to Life Beyond Seen, where curiosity takes a deep breath and slips beneath the waves, and science prefers a slower current as it drifts towards sleep. Tonight, we're setting out on a journey that's been unfolding for hundreds of millions of years, through a world where the ancient still hunts and the primeval never truly ended. It's easy to think of the ocean as a place of constant change, of evolving life and shifting tides, but beneath its glittering surface lives a gallery of creatures that have barely changed since long before the first humans walked the earth. They are the old ones, the veterans of evolution, the hunters that learned how to survive in the dawn of time and saw no reason to stop. As we follow them through the darkness of the deep and the stillness of the shallows, we might find that the story of life isn't always about relentless change. Sometimes it's about finding what works and keeping it. Before we dive too deep into this ocean of stories, I'd love to know something small and personal. Where are you listening from tonight? Somewhere near the coast, perhaps where the salt air carries hints of the sea, or far inland, where the idea of the deep ocean feels as distant as another planet. Wherever you are, the waters we're about to explore are the same waters that have cradled life for over 3 billion years, and tonight they hold the key to one of nature's most fascinating secrets. If you find this kind of slow exploration soothing, if you like drifting through science that lulls instead of lectures, I'd be grateful if you gave this video a like and maybe subscribed. It helps this little corner of curiosity find others who might want to wander through the quiet together. Now, let's breathe deeply and begin, because somewhere beneath the waves, older than empires, older even than bones, the ancient hunters are still waiting. The story begins long before anything that looked like us existed, before dinosaurs thundered across continents or trees shaded the land. In the Precambrian seas, more than 500 million years ago, life was already experimenting with forms and strategies, and among those experiments were hunters. They weren't hunters the way we think of them now, sleek and toothed and muscular. They were simple, often soft-bodied, drifting or crawling through primeval oceans. But they were the first creatures to pursue other living things for food, and that pursuit shaped everything that followed. Predation is one of the oldest dramas in life's story, and it set off an evolutionary arms race that never stopped. Shells hardened, senses sharpened, bodies streamlined and strengthened, and while countless species came and went, a surprising number of those early designs proved so successful that they're still with us today, barely altered by time. This is the quiet marvel of what biologists call living fossils, though that name can be a bit misleading. These are not fossils in the sense of being dead or frozen in time. They are living, breathing organisms that continue to thrive in modern ecosystems. What makes them remarkable is that their basic body plans, their hunting strategies, and often their genetic blueprints have remained largely unchanged for tens or even hundreds of millions of years. Evolution didn't stop for them, but it slowed, fine-tuned and settled into a pattern that worked. Like a tool perfected so early it never needed replacing, these creatures demonstrate that in nature, success doesn't always mean novelty. Sometimes it means stability. It's worth asking why some organisms change rapidly over evolutionary time, while others remain so steadfastly the same. Part of the answer lies in their environments. The deep ocean, especially, is one of the most stable habitats on Earth. Temperatures barely fluctuate. Light is scarce or absent. Pressures are immense but constant. Over millions of years, such conditions can create evolutionary havens, where well-adapted forms persist with little pressure to change. Another factor is how well an organism's basic design fits its niche. If a creature is already exquisitely suited to its way of life, natural selection has little reason to reinvent it. Instead, small refinements may occur over time, but the overall blueprint remains. Consider the nautilus, a small spiral-shelled cephalopod that looks almost like a piece of ancient jewellery drifting through the water. It first appeared over 500 million years ago, long before fish had jaws and before plants had colonised the land. Yet if you were to hold a nautilus today and compare it to its distant ancestors, you'd see a striking resemblance. Its chambered shell, its tentacled body, its slow, deliberate way of moving through the water, all of it is nearly the same. The nautilus hunts by stealth and patience, using its tentacles to grasp prey, and its simple but effective eyes to detect movement. It hasn't needed speed or strength, because its deep-sea habitat rewards economy and precision. In a world where energy is precious and prey can be scarce, the Nautilus's ancient design is still perfectly fit for purpose. It's not alone. In shallow coastal waters and muddy estuaries, another ancient hunter scuttles quietly beneath the waves, the horseshoe crab. Its lineage stretches back more than 450 million years, predating even the first dinosaurs. Despite its name, it's not a crab at all, but a closer relative of spiders and scorpions. And yet, its strategy for survival is timeless. Its hard, domed exoskeleton protects it from predators. Its array of legs and pincers let it scavenge and capture small prey. Most importantly, it plays a crucial role in modern ecosystems, and even in modern medicine. Horseshoe crab blood, rich in copper and sensitive to bacterial toxins, is used to test the safety of vaccines and medical equipment. This ancient creature, armoured in a design that's barely changed since the Ordovician, still touches human lives in ways its earliest ancestors never could have imagined. Then there are the sharks, the quintessential ocean hunters whose story spans more than 400 million years. Long before the first dinosaurs appeared, sharks were already patrolling ancient seas, and while their diversity has exploded and their forms have shifted, the core blueprint remains astonishingly consistent. Streamlined bodies, keen senses, replaceable teeth, and a cartilaginous skeleton make them efficient, adaptable predators. They've survived multiple mass extinctions, dramatic climate shifts, and changing ocean chemistries. Today, sharks range from the small and secretive to the massive and fearsome. But each one carries in its body the legacy of an ancient design honed to near perfection. Some hunters, like this coelacanth, were thought to have vanished entirely until they surprised us by reappearing. Known only from fossils for over 60 million years, the coelacanth was believed to be extinct until a living specimen was caught off the coast of South Africa in 1938. Its lobe-finned body, its peculiar walking fins, and its deep-sea habitat all speak to a lineage that has changed little since the Devonian period. While not a fast or aggressive predator, the coelacanth remains a formidable ambush hunter, lying in wait for unsuspecting prey in the darkness of deep reefs. Its rediscovery was not just a scientific shock, but a reminder that the ocean still holds secrets, and that the ancient is not always gone. Reptilian hunters have their own enduring representatives. Crocodilians, including crocodiles and alligators, trace their ancestry back over 200 million years. They shared the earth with the earliest dinosaurs and watched them rise and fall, yet they remain apex predators today. Their success lies in a design that is both powerful and patient. Streamlined bodies, powerful jaws, stealthy ambush tactics, and the ability to survive long periods without food make them masters of rivers and coasts. Though some details have evolved, the crocodilian silhouette would be instantly recognizable to any creature from the Mesozoic. Not all ancient hunters rely on complex anatomy. The jellyfish, for instance, is a predator of extraordinary simplicity and age. Fossils of jellyfish-like creatures date back more than 500 million years, and their basic body plan, a gelatinous bell and trailing tentacles armed with stinging cells, remains almost unchanged. They drift with currents, capturing plankton, fish larvae, and even small fish in their nematocyst-laden tentacles. Despite lacking a brain, heart, or bones, jellyfish dominate vast stretches of the ocean. Their success proof that complexity isn't always the key to survival. They are ancient hunters that float more than chase, that ensnare rather than pursue, and yet they thrive. Other cephalopods took a different evolutionary path from the nautilus, shedding their shells and embracing speed, intelligence, and adaptability. Squids and octopuses, descendants of ancient shelled ancestors, became some of the ocean's most sophisticated hunters. Their lineage stretches back nearly as far as the nautilus, and though their forms are more modern, the core evolutionary toolkit, tentacles, keen senses, and remarkable neural processing, is deeply ancient. They are shapeshifters and problem solvers, capable of dazzling displays of camouflage and complex hunting strategies, yet their success is rooted in principles first tested hundreds of millions of years ago. Even creatures we don't often think of as predators, like sea turtles, have ancient hunting stories to tell. Their lineage extends back to the age of dinosaurs, and while many are herbivores or omnivores, others are skilled hunters of jellyfish, crustaceans, and fish. Their slow, deliberate movements and incredible migratory journeys are not signs of weakness, but of evolutionary refinement. Over millions of years, they've balanced vulnerability and strength, persistence and patience, becoming enduring presences in the oceans they've crossed for eons. The persistence of these ancient hunters tells us something profound about evolution. Change is not inevitable, and progress is not always measured by novelty. In some cases, the earliest solutions nature devised remain the best. When an organism fits its niche so well that environmental shifts and competition cannot dislodge it, evolution may favour stability over innovation. These creatures are not relics of a bygone world. They are active participants in the present, their bodies and behaviours refined by unimaginable spans of time. Their survival also challenges our perception of what it means to be ancient. We often think of ancient as synonymous with obsolete, as if old designs must eventually be replaced. But the ocean shows us another truth. Age can mean resilience, endurance, and a proven capacity to adapt just enough without losing what works. These creatures remind us that survival isn't about constant reinvention. It's about balance, between change and continuity, between adaptation and stability. It's tempting to view the story of life as a relentless march forward, each generation replacing the last with something newer, faster, smarter. But the ancient hunters of the deep reveal a subtler story. Evolution is not a straight line, but a branching, twisting path, where some branches grow rapidly and others remain steady. Some lead to dead ends, while others persist for hundreds of millions of years. And those that endure do so not by being static, but by being exquisitely tuned to their worlds. As we descend further into this story, deeper into the ocean and deeper into time, we'll meet these survivors one by one, exploring how each found its way through extinction events, shifting climates, and relentless competition. Their stories are windows into Earth's distant past, but they are also mirrors reflecting the principles that govern life today. The Nautilus's quiet patience, the shark's relentless efficiency, the jellyfish's elegant simplicity. Each offers a lesson about survival, not just in the ocean, but in the larger story of life. And as we trace their journeys through time, we may begin to see our own species differently. Humans like to think of ourselves as the pinnacle of evolution, but compared to these ancient hunters, we are newcomers, recent arrivals in a story that began long before we could measure it. They have weathered cataclysms that would obliterate us. They have thrived in worlds alien to our own, and they will likely continue long after we're gone. Their endurance is humbling, a reminder that life's greatest strength often lies not in its newest inventions, but in its oldest ones. So let's keep following the current, deeper into the dark where sunlight fades and pressure rises, where the oldest hunters still glide and pulse and wait. Their stories have no sharp beginnings and no neat endings. They are continuous, like the ocean itself, vast, patient, and alive. And in that continuity, there is something profoundly comforting. Evolution is not just a story of change, it is also a story of endurance, of forms so perfect they need no reinvention. Down here, In the deep and the dark, the past is not gone. It swims beside us, hunts beside us, and shows us that in nature, ancient does not mean obsolete. It means proven. And so, with the surface far above, and the weight of time pressing gently all around, we move forward, or perhaps downward, into the next layer of this story, because the deep still holds more secrets, and the oldest hunters are only just beginning to reveal themselves. If the ocean today feels like a place of ceaseless movement, of restless tides and darting life, it's easy to forget that much of what swims through it has been here far longer than we have names for the seas themselves. The creatures we call ancient are not ghosts in the sense of being gone, nor are they relics frozen in some distant past. They are living links across unthinkable spans of time, the survivors of catastrophes that reset the world, the bearers of designs tested against every cruelty Earth could offer. They move quietly among us, indifferent to our brief histories, and in their continued presence they tell stories that reach back to the dawn of complex life. These ghosts of deep time are not spectres but witnesses, still hunting, still thriving, their bodies and instincts carrying echoes of worlds long vanished. To understand just how remarkable their persistence is, we have to stretch our imagination beyond the familiar scale of years or centuries and into the deep chronology of the planet. Earth formed roughly 4.5 billion years ago. For most of that time, life was simple, microscopic, single-celled, and unseen. It wasn't until about 541 million years ago, during an event known as the Cambrian explosion, that complex multicellular life suddenly diversified in astonishing ways. In a relatively short geological moment, new forms of movement, predation, and defense emerged. Mouths and eyes appeared. Creatures swam, burrowed, and stalked. Ecosystems grew more complex and dynamic. It was here that many of the body plans and survival strategies we still see today first took shape, and among them were predators, the first active hunters, organisms that didn't just filter nutrients from the water, but actively pursued and consumed other living things. Some of those early predators vanished, leaving only fossilized impressions in shale and limestone. Others evolved into forms unrecognizable from their ancestors, but a few lines endured with astonishing fidelity, weathering 5 mass extinctions and countless environmental upheavals. These are the creatures we call living fossils, though the term has its critics. It can suggest stasis, as if these species have been completely unchanged, which is rarely true. Evolution never fully stops, but it can slow dramatically, and in these lineages the fundamental body plan, the architecture of muscles, skeleton, nervous system, and instinct remains so close to its ancient form that a creature from 500 million years ago would recognize its kin today. One of the most famous examples is the nautilus, whose spiral shell and slow deliberate movements have graced the oceans for more than 500 million years. Imagine that span. This lineage predates fish with jaws, trees, flowering plants, dinosaurs, and mammals. When the supercontinent Pangaea formed and broke apart, when volcanic eruptions darkened the skies and meteors slammed into the earth, the nautilus persisted. Its strategy is simple but effective. It uses jet propulsion to move, drawing water into its mantle cavity and expelling it through a siphon. Its shell is divided into chambers that it can fill with gas or water to control its buoyancy, allowing it to rise and fall with minimal effort. It hunts small prey like crustaceans and fish by extending its many tentacles, which are sticky and strong, perfect for grasping. Its eyes, though primitive compared to ours, are sensitive to light and movement, more than enough for the dim environments it inhabits. This combination of efficiency, protection, and economy has kept the nautilus thriving while countless other species rose and fell. The nautilus is not just an evolutionary curiosity. It is a living connection to an ancient world that looked nothing like ours. When its ancestors first appeared, there were no vertebrates, no land animals, no flowering plants. The continents were barren, the skies devoid of birds. And yet, in the dark waters of the Paleozoic seas, predators like the nautilus hunted and fed much as they do now. That continuity is more than just a biological footnote. It is evidence of how natural selection shapes life, not just by driving change, but by preserving what works. If the nautilus is a symbol of patience and precision, the horseshoe crab is a monument to endurance. Its lineage extends back some 450 million years, making it older than dinosaurs, older than trees, and older than the very continents as we know them. Horseshoe crabs scuttled across ancient seabeds, while trilobites still dominated the oceans. They survived the Permian extinction, an event so catastrophic that it wiped out over 90% of marine species. They endured the asteroid impact that ended the reign of the dinosaurs, and today they continue to thrive in shallow coastal waters around the world. Part of their success lies in their rugged simplicity. Their hard, curved exoskeleton provides protection from predators and rough environments. Their book gills, feathery structures on the underside of their bodies, allow them to breathe both in water and on land for short periods, giving them flexibility in where they can live and spawn. Their compound eyes, while not as sophisticated as those of modern insects, are sensitive to light and movement, helping them navigate and avoid threats. And their feeding strategy, scavenging for worms, mollusks, and small crustaceans, has remained virtually unchanged. But perhaps most remarkable is their blood. Horseshoe crab blood contains a substance called limulus amebocyte lysate, which clots in the presence of bacterial endotoxins. This property is so sensitive that it's used to test the sterility of medical equipment and vaccines. Every time a syringe or implant is certified as safe, the blood of an ancient hunter has played a part. Horseshoe crabs remind us that survival is not always about speed or aggression. Sometimes it's about resilience, about being able to weather the slow violence of time. Their bodies are not flashy or fast, but they are robust, versatile, and astonishingly well suited to their ecological niche. They are living proof that nature's oldest designs are not primitive but perfected. Sharks tell a similar story, but from a different angle. They're not passive survivors, but active, relentless hunters. Their ancestors first appeared over 400 million years ago, and though modern sharks vary widely in size, shape, and behaviour, the essential shark blueprint, a streamlined body, a cartilaginous skeleton, rows of replaceable teeth, and acute senses, has remained stable. Sharks' sensory abilities, particularly their ability to detect electrical fields produced by other animals, give them a hunting edge few predators can match. Their cartilage skeleton makes them lighter and more flexible than bony fish, allowing for swift bursts of speed and agility. And their reproductive strategies, ranging from live birth to egg laying, ensure their survival across a range of environments. Over the course of their long history, sharks have survived 2 of the 5 great mass extinctions, adapted to new prey and new competitors, and colonized nearly every marine habitat on Earth. Some, like the frilled shark, retain features so ancient they look almost unchanged from their Devonian ancestors. Others, like the great white, represent the pinnacle of predatory refinement. But all share the same evolutionary roots, a lineage that has outlasted empires and ice ages alike. Then there are the creatures that disappeared from our awareness, only to reappear centuries later, like whispers from the deep. The coelacanth is the most famous of these. Known only from fossils and believed to have gone extinct 66 million years ago, it was rediscovered alive in 1938 off the coast of South Africa. Its discovery stunned the scientific world. Here was a fish that had survived unchanged for more than 360 million years, a living representative of a lineage that once gave rise to the first amphibians. The coelacanth's lobed fins, which resemble the limbs of early land vertebrates, provide a rare glimpse into the evolutionary transition from water to land. Its hunting strategy, lurking near deep-sea caves and ambushing prey, is as ancient as its form. It is a ghost of deep time made flesh again, a reminder that extinction is sometimes only apparent and that the ocean still hides survivors from forgotten ages. Crocodilians tell another story of persistence and adaptation. Their lineage stretches back more than 200 million years, to a time when dinosaurs had just begun their rise. Early crocodilian relatives were diverse, some terrestrial, some fully marine, some even herbivorous. But the modern crocodile's form, low-slung, armoured and amphibious, emerged early and has changed little since. Their hunting strategy too remains largely the same: patience, stealth and explosive power. They wait, often motionless, near the water's edge until prey ventures too close, then strike with astonishing speed. Their powerful jaws, sensitive to the slightest vibration, clamp down with bone-crushing force. Their physiology allows them to slow their metabolism, enabling them to survive long periods without food, a crucial adaptation in environments where meals can be unpredictable. Like sharks, they are apex predators, and like sharks, they embody a design so effective that evolution had little reason to alter it. But perhaps the most surprising of the ancient hunters are those that seem barely alive at all. Jellyfish, for example, are among the oldest multicellular animals on Earth. Fossils resembling modern jellyfish date back more than 500 million years, and their basic structure, a gelatinous bell and stinging tentacles, has remained consistent. They are predators of a different kind, lacking brains, bones or hearts, yet capable of capturing prey with remarkable efficiency. Their tentacles are lined with nematocysts, specialized cells that deliver venom to paralyze or kill. They drift with the currents, passive yet deadly, their success rooted in simplicity rather than sophistication. In a world where predators often evolve greater complexity to outcompete their prey, jellyfish show that minimalism can be just as powerful a strategy. The persistence of these creatures across geological time speaks to the varied ways evolution solves the problem of survival. Some refine their tools to razor-sharp precision. Others rely on endurance and resilience. Some evolve complex sensory systems and neural networks. Others dispense with such complexity altogether. What they share is not a particular form or strategy, but a record of success measured in hundreds of millions of years. They are the survivors of mass extinctions that reshaped the planet, of shifting continents and climates, of new predators and prey. They have adapted not by constant transformation, but by honing their advantages until they were nearly unbeatable. Their survival also tells us something important about the nature of change itself. We often imagine evolution as a ladder, each rung a step toward greater complexity or intelligence. But it is not a ladder. It is a branching tree, and some branches grow slowly, changing little because they do not need to. These branches are not lesser or stagnant. They are stable, enduring, and deeply successful. The creatures that inhabit them are not evolutionary throwbacks, but masters of their chosen strategies. And yet, calling them unchanged is not entirely accurate. Even the most ancient lineages continue to evolve, albeit subtly. Genetic mutations accumulate, behaviours shift, small adaptations emerge. The difference is that these changes occur within a framework that has already proven highly effective. The Nautilus may look much as it did 500 million years ago, but its shell composition, metabolic processes, and reproductive strategies have all evolved in ways that allow it to cope with modern conditions. Sharks, too, continue to diversify, developing new hunting techniques and filling new ecological niches. Stability and change are not opposites in evolution. They are partners, each shaping the other in response to the pressures of the environment. The endurance of these ancient hunters also raises intriguing questions about the future. If their designs have lasted this long, how much longer might they persist? Will sharks still patrol the oceans 100 million years from now? Will nautiluses still drift in the deep? Will jellyfish still pulse beneath the waves long after our species is gone? It's impossible to know for certain, but their track record suggests that many will. They have already survived conditions far harsher than those we face today. They have adapted to changes in temperature, sea level, oxygen, and chemistry. Their resilience is woven into their biology. For us, these creatures offer more than just scientific curiosity. They are windows into Earth's distant past, living archives of evolutionary history. Studying them helps scientists reconstruct ancient ecosystems, understand how life adapts over deep time, and even predict how modern species might respond to future changes. The coelacanth, for example, has reshaped our understanding of the transition from aquatic to terrestrial life. Horseshoe crab blood continues to save human lives. Sharks' immune systems inspire medical research. Even jellyfish, simple as they seem, are teaching us about neural networks, regeneration, and even the aging process. There is also something humbling in their presence. We humans tend to think of ourselves as the pinnacle of evolution, the most advanced species on Earth. But compared to these creatures, we are newcomers, recent arrivals in a drama that has been unfolding for hundreds of millions of years. They have survived cataclysms we can scarcely imagine. They have thrived in worlds alien to our own, and they will likely endure in some form long after we are gone. In their persistence, they remind us that survival is not about dominance or intelligence alone. It is about fit. About finding a way of being that works and holding on to it. As we move deeper into this story, the ghosts of deep time will guide us through the next layers of life's history, from the early cephalopods that mastered buoyancy to the armoured hunters that claimed both land and sea. Their stories are not separate chapters but continuous threads woven through the fabric of life on Earth. And if we follow those threads closely enough, we may not just learn about them, we may also learn something about ourselves, about what it means to endure, to adapt, and to belong to a story far larger and older than our own. The ocean holds many such stories, each hidden in the curve of a shell, the pulse of a bell, the glint of an ancient eye. And as we continue downward into its depths, we'll find that these ghosts are not fading. They are still here, still hunting, still shaping the world in ways we're only beginning to understand. Among the many ancient hunters that still patrol the deep, few capture the imagination quite like the Nautilus. It is a creature so old that its ancestors were swimming through primordial seas hundreds of millions of years before the first dinosaurs took their first steps on land. It is not fierce in the way sharks are fierce, nor swift like a squid slicing through the water, but it is a hunter nonetheless, one that has endured not by dominating the ocean with strength, but by perfecting a slower, subtler approach. To see a nautilus drift in the dim blue light of the deep is to look directly into the past, to watch a living design that predates most complex life on Earth continue its patient, deliberate work. And in its spiral shell and careful movements, we can trace an unbroken lineage stretching back over 500 million years, a span of time so vast it almost defies comprehension. The nautilus belongs to a group of animals known as cephalopods, a class that also includes octopuses, squids, and cuttlefish. Today, cephalopods are known for their intelligence, agility, and ability to change shape and colour in the blink of an eye. But the nautilus represents a much older branch of this family tree. While its modern relatives have shed their external shells and embraced speed, stealth, and cunning, the nautilus retains the ancestral blueprint, a coiled, chambered shell, a simple hunting strategy, and a lifestyle that has remained remarkably consistent for hundreds of millions of years. In that sense, it is a time capsule, not frozen or stagnant, but carrying with it the traits that first made cephalopods successful predators in Earth's ancient seas. The origins of the nautilus stretch back to the late Cambrian or early Ordovician period, more than 500 million years ago. At that time, life in the oceans was exploding in diversity. Trilobites crawled along the seafloor. Early fish without jaws filtered nutrients from the water. Primitive arthropods swam and crawled in a riot of new forms, and among them appeared the first cephalopods, straight-shelled hunters called orthocones that used jet propulsion to move and tentacles to capture prey. These early cephalopods were the apex predators of their time, formidable hunters in an ocean where few organisms had evolved defences against such speed and precision. Over millions of years, some of these straight shells began to coil, forming the spiral shape we now associate with the nautilus. The coiled shell was more than just a cosmetic change. It improved buoyancy control, made the animal more manoeuvrable, and allowed it to occupy new ecological niches. That innovation, simple though it may seem, proved so effective that it remains at the heart of the Nautilus's design today. The nautilus shell is one of the most remarkable structures in the natural world. From the outside, it appears as a smooth, elegant spiral, its surface often marked with delicate patterns of cream and brown. Inside, however, it is a marvel of engineering. The shell is divided into a series of chambers, each sealed off from the others. The nautilus itself occupies the largest, outermost chamber, while the inner ones are filled with a carefully regulated mixture of gas and liquid. By adjusting the ratio of gas to fluid in these chambers, the nautilus can control its buoyancy with exquisite precision. It can rise or sink in the water column without expending much energy, a critical advantage in the deep ocean, where conserving energy can mean the difference between survival and starvation. The animal moves using a simple but effective form of jet propulsion. It draws water into a cavity within its mantle, and then expels it forcefully through a siphon, propelling itself in the opposite direction. This method of movement is not fast compared to modern cephalopods, but it is efficient and quiet, ideal for a creature that hunts by stealth and patience. The nautilus is not a chaser, it is an ambush predator, drifting slowly through the water until an unsuspecting prey item wanders too close. Then, in a sudden burst of movement, it extends its many tentacles to seize the meal. Those tentacles are another example of the nautilus's ancient design. Unlike the muscular, suction-cupped limbs of squids and octopuses, nautilus tentacles are simple and sticky, lacking suckers but equipped with fine ridges that help them grip. A fully grown nautilus can have up to 90 of these slender appendages, which it uses to grasp prey such as small crustaceans, fish and carrion. Once captured, the prey is drawn toward a beak-like mouth, where it is broken down and consumed. It is a straightforward strategy, one that has changed little in hundreds of millions of years, because it has never stopped working. The Nautilus's sensory systems reflect its ancient lineage as well. Its eyes, for example, are far simpler than those of its modern cephalopod relatives. They lack a lens and function more like a pinhole camera, forming images through the amount of light that enters a small opening. By human standards, this makes for poor vision, but in the dim environments where the nautilus lives, often hundreds of meters below the surface, it is more than adequate. The nautilus relies less on detailed visual information and more on detecting movement and contrast, which is enough to identify prey and avoid predators. Its sense of smell is also well developed, and likely plays a significant role in locating food. Perhaps most remarkable of all is the nautilus's internal clock. These creatures rise and fall in the water column in a daily rhythm, ascending toward shallower waters at night to feed, and descending again into deeper, darker zones during the day. This behaviour, known as diel vertical migration, helps them avoid predators and take advantage of food sources that move closer to the surface under cover of darkness. It is a rhythm as old as the ocean itself, a daily pulse that has been beating since long before humans existed to notice it. For all its elegance, the nautilus is not without vulnerabilities. Its reproductive strategy, for one, is slow and conservative. Nautiluses take many years, sometimes more than 15, to reach maturity, and females produce relatively few eggs. Those eggs are large and encased in tough shells, but they can take up to a year to hatch. This slow reproductive rate makes nautilus populations particularly sensitive to environmental changes and human pressures. In recent decades, overfishing for their beautiful shells has driven some populations into decline. Climate change and ocean acidification, which can affect shell formation, pose additional threats. These pressures are reminders that even designs honed over 500 million years are not immune to sudden, human-driven changes in the environment, and yet the Nautilus endures. It has survived mass extinctions that wiped out the majority of life on Earth. It has persisted through global ice ages, volcanic cataclysms, and the slow drift of continents. Its resilience lies in its balance of simplicity and sophistication. It is not fast, but it is efficient. It is not aggressive, but it is patient. It is not widespread, but where it lives, it fits perfectly. Evolution has little reason to overhaul a design that works this well. The Nautilus also offers us a rare window into the deep history of life. Fossils of ancient nautiloids, the group to which the Nautilus belongs, are abundant in rocks hundreds of millions of years old. By comparing these fossils to living nautiluses, scientists can trace how cephalopods evolved over time. They can see when shells coiled, when buoyancy systems became more refined, when different hunting strategies emerged. In a sense, every living nautilus is both a predator and a paleontological tool, a bridge between the ancient seas and the modern ones. Their story also helps us understand a broader truth about evolution, that it is not always about progress toward complexity or intelligence. The Nautilus is far simpler than a squid or octopus. It lacks their sophisticated eyes, their problem-solving brains, their rapid colour-changing skin, and yet, in its environment, its simplicity is an advantage. Its shell provides protection and buoyancy. Its slow metabolism suits the sparse resources of the deep. Its reproductive strategy, while slow, ensures that its offspring are well developed and ready to survive. Complexity is not inherently better, fitness is, and the Nautilus is profoundly fit for the life it leads. Even its shell, often admired for its beauty, is more than a piece of natural art. Its internal structure follows a mathematical pattern known as a logarithmic spiral, which allows the shell to grow without changing shape. As the Nautilus grows, it adds new chambers to its shell and moves into the outermost one, sealing off the older chambers behind it. Each chamber is slightly larger than the last, maintaining the same proportions as the animal matures. This growth pattern is not only efficient but also elegant, a physical manifestation of evolutionary refinement. It's a reminder that beauty in nature often arises as a byproduct of function, that what is most pleasing to our eyes is often what works best in the natural world. There's a curious irony in how humans have interacted with the Nautilus. For centuries, its shells have been prized as objects of beauty and symbols of perfection. Artists, mathematicians, and philosophers have marvelled at their spirals, seeing in them reflections of harmony and order. Yet in our admiration, we have also endangered the very creatures we celebrate. Shell collecting, once a small-scale curiosity, became a commercial industry, and Nautilus populations in some regions suffered. Efforts are now underway to protect them. With some species listed under international conservation agreements, it is a delicate balance, one ancient hunter trying to survive in a world dominated by a new one. The Nautilus also challenges our assumptions about intelligence and success. Modern cephalopods like octopuses are celebrated for their problem-solving skills, their tool use, their apparent curiosity. The Nautilus, by contrast, shows little of this behavioural complexity, and yet, measured in evolutionary terms, it is every bit as successful. It has outlived countless species more advanced than itself. It has endured while empires rose and fell, while continents drifted and climates changed. It has persisted not by outthinking its prey or its predators, but by fitting its niche so well that change was unnecessary. It is a reminder that intelligence is just one of many strategies life uses to survive, and not always the most enduring. The Nautilus's long history, also intersects with the story of humanity in subtle ways. Its fossils have helped scientists calibrate the geological timeline, offering clues about the environments of ancient Earth. Its living relatives provide insights into how buoyancy control evolved, a key adaptation that allowed cephalopods to become the versatile predators they are today. And its conservation story reflects our growing awareness of how human actions ripple through ecosystems, an awareness that may determine whether this ancient lineage continues its journey into the future. When we watch a nautilus drift through the dim water, we are seeing more than just a single creature. We are watching a lineage that has endured through almost every chapter of life's story. We are seeing a design that emerged in the early Paleozoic and still works in the modern ocean. We are looking at a predator that hunts not with speed or strength but with patience and precision. And we are glimpsing the vastness of deep time made tangible, not as a fossil locked in stone, but as a living, moving presence. Its story is not over, and it is not isolated. The Nautilus is one thread in a vast tapestry of ancient hunters, each with its own strategy, its own adaptations, its own lessons. As we follow those threads deeper into the ocean and further into the past, we begin to see how many of the principles that guide life today were established long before we appeared. The Nautilus teaches us about patience and persistence, about the power of simplicity, about the elegance of designs that endure. But it also points us forward toward other ancient hunters whose paths have been different, but whose stories are just as compelling. Some shed their shells and embraced speed. Others grew armour and took to the shallows. Some grew large and powerful. Others remained small and subtle. Together, they form a living museum of evolution, a reminder that the ocean story is not just about what is new, but also about what has lasted. And so, from the slow, spiralling drift of the Nautilus, our journey continues outward and onward, toward the next of these survivors, creatures armoured in ancient design, crawling across the seabed in forms that time itself has barely touched. If the Nautilus represents the patient precision of ancient hunters, then the horseshoe crab embodies something even more fundamental, the sheer, stubborn resilience of life that refuses to yield. Its story is one of extraordinary endurance, a saga that began nearly 500 million years ago and continues to this day with barely a pause. In an ocean that has transformed countless times, where continents have split and collided, where temperatures have risen and fallen and species have come and gone in waves of extinction, the horseshoe crab has remained. It scuttled across seafloors before the first trees rooted themselves in soil. It spawned beneath the moonlight while trilobites still ruled the oceans. It witnessed the rise of dinosaurs and their fall, the birth of mammals, and the emergence of humans. And through it all, it changed very little. It is not simply old, it is ancient beyond easy comprehension, a survivor from a world so alien, it might as well be another planet. At first glance, the horseshoe crab does not look like a hunter at all. Its domed shell, long tail spine, and small probing legs give it an appearance more suited to a relic of science fiction than a modern predator. And in truth, it is neither fish nor crab nor even a crustacean. Its closest living relatives are spiders and scorpions. The horseshoe crab belongs to a group called chelicerates, a lineage that diverged from the ancestors of insects and crustaceans more than 500 million years ago. That alone makes it remarkable. It is not just old, it is part of a branch of the tree of life that split before most of the animals we recognise today even existed. And yet, despite this deep evolutionary separation, the horseshoe crab thrives in coastal waters around the world, especially along the Atlantic shores of North America and the Indo-Pacific. Its anatomy is a testament to evolutionary efficiency. The horseshoe-shaped carapace that gives the animal its name is a tough, protective shield that guards its soft underside and vulnerable organs. This exoskeleton is not merely armour against predators, it also helps the animal burrow into sediment and navigate turbulent shallows. Beneath the shell lies a cluster of jointed legs ending in pincers perfectly suited for grasping and tearing apart small prey. The horseshoe crab's mouth is located in the centre of these legs, so it effectively walks its food into its mouth as it moves, a simple, effective feeding method that requires little energy. Its tail spine, called a telson, looks dangerous, but is not a weapon. Instead, it serves as a rudder for steering and balance, and it helps the animal right itself if it's flipped upside down by waves or predators. The horseshoe crab's eyes, meanwhile, are scattered across its shell. It has 2 large compound eyes on top that detect movement and light, 5 additional eyes arranged along the shell to track lunar cycles and other light-sensitive structures near its mouth and tail. This array of vision organs is particularly important because horseshoe crabs synchronize much of their behavior, including reproduction, with the phases of the moon and the tides. When it comes to hunting, the horseshoe crab is not a sprinter or a chaser. Its strategy is one of steady foraging, probing through sand and mud for worms, mollusks, and other small invertebrates. Its legs, tipped with small claws, sift through sediment, pulling food toward its central mouth. It can detect chemical cues in the water, helping it locate prey even when visibility is low. And because it can tolerate a wide range of salinities and oxygen levels, it thrives in estuaries, tidal flats, and other dynamic environments where food is abundant but conditions change rapidly. This adaptability has been key to the horseshoe crab's survival over the eons. The environments it inhabits, shallow coastal waters, are among the most changeable on Earth. They are subject to tides, storms, temperature swings, and fluctuations in salinity. They are the first to feel the impact of continental shifts, sea level changes, and ice ages. Many species that once dominated these habitats vanished as conditions changed. The horseshoe crab did not. Its ability to tolerate extremes, combined with its protective armour and simple but effective lifestyle, allowed it to ride out upheaval after upheaval. One of the most striking aspects of the horseshoe crab's life cycle is its connection to the tides and the moon. Every spring and summer, thousands of horseshoe crabs gather on sandy beaches to spawn, often under the light of a full or new moon. Females crawl ashore and dig shallow nests, laying thousands of small greenish eggs in the sand. Males, smaller and more numerous, cling to the females' shells or swarm around them to fertilize the eggs as they are laid. The timing is precise, coordinated with high tides that carry the crabs closer to the shore and give their offspring the best chance of survival. This mass spawning event is more than just a reproductive ritual. It is a cornerstone of coastal ecosystems. The eggs, laid in vast numbers, are a crucial food source for migratory birds, fish, and other animals. For millions of shorebirds travelling from South America to the Arctic, the horseshoe crab spawning season is a life-saving stopover, providing the energy they need to complete their long journeys. In this way, the horseshoe crab is not just an ancient hunter, but also a keystone species, its life woven into the rhythms of countless others. Beyond its ecological role, the horseshoe crab has an unexpected connection to human health. Its blue blood, blue because it uses copper, not iron, to transport oxygen, contains a substance called limulus amebocyte lysate, LAL. This substance reacts violently to bacterial endotoxins, forming a clot even in tiny concentrations. Medical researchers discovered this property in the 1950s, and since then, LAL has become essential for testing the sterility of medical equipment, vaccines, and intravenous drugs. Every batch of these products must be checked to ensure it is free of contamination, and horseshoe crab blood remains one of the most reliable tools for doing so. In this way, a creature that evolved long before humans existed now plays a direct role in modern medicine, saving lives in ways unimaginable to its ancient ancestors. This connection is not without consequences. The biomedical industry collects hundreds of thousands of horseshoe crabs each year, bleeding them for LL before releasing them back into the wild. While many survive, some do not, and scientists continue to study the long-term impact of this practice on populations. Conservationists are also exploring synthetic alternatives to LAL, which could reduce reliance on wild horseshoe crabs. Once again, a lineage that has weathered 500 million years of natural upheaval now faces a challenge it has never encountered before: the pressures of human activity. Despite these pressures, horseshoe crabs remain remarkably resilient. They are survivors of 5 mass extinctions, including the catastrophic Permian-Triassic event 252 million years ago, which wiped out the majority of marine life. They endured the asteroid impact that ended the age of dinosaurs. They persisted through ice ages and warm periods, rising and falling seas and shifting coastlines. Their endurance speaks not just to the strength of their design, but to the power of evolutionary strategies that prioritize flexibility and resilience over specialization. The horseshoe crab is not a creature that excels in narrow circumstances. It is one that thrives across a broad range of them. Its fossil record tells a story of remarkable continuity. Ancient horseshoe crabs from the Ordovician and Silurian periods look strikingly similar to those alive today. Their basic body plan, a domed carapace, jointed legs, tail, spine, and cluster of eyes, has remained intact for hundreds of millions of years. This is not because evolution has ignored them, but because the pressures they face have not required radical change. The environments they inhabit remain dynamic but fundamentally similar. Their prey remains small and plentiful. Their predators have come and gone, but their armour continues to provide effective defence. In a world where so much changes, the horseshoe crab stands as a testament to the value of staying the same. That does not mean they are static. Subtle changes continue to occur. Modern horseshoe crabs, for example, have evolved reproductive strategies and shell shapes suited to their specific habitats. Populations in Asia differ from those in North America, reflecting millions of years of separate evolutionary history. These variations remind us that even the most ancient lineages are not frozen in time. They are dynamic, adapting at a pace that matches the stability of their environments. The horseshoe crab story also highlights an important truth about evolution. Success is not measured by how fast a species changes or how complex it becomes. It is measured by how well it survives. By that measure, the horseshoe crab is one of Earth's greatest success stories. Its lineage has persisted through almost unimaginable spans of time, navigating changes that wiped out most of the species it once shared the planet with. It has done so not by being the biggest or the fastest, but by being tough, adaptable, and exquisitely suited to its niche. In many ways, the horseshoe crab is a bridge between the ancient world and the modern one. It connects us to ecosystems that existed long before humans appeared. It links the evolutionary history of marine arthropods to the terrestrial arachnids and insects that would later dominate the land. And it ties the deep past to the present in a very practical way, through its ongoing role in medicine and ecology. To watch a horseshoe crab crawl along a tidal flat today is to see a piece of Earth's deep history still very much alive. Its ancientness can be difficult to grasp. Think of the timeline. When the first horseshoe crabs scuttled through shallow seas, trilobites, those iconic Paleozoic arthropods, were still abundant. The first land plants were only just beginning to colonize damp shorelines. Fish had not yet evolved jaws. The continents were arranged in patterns unfamiliar to us, and the air contained no oxygen-rich ozone layer. Through all the changes that followed, the rise of forests, the formation and breakup of supercontinents, the emergence of dinosaurs, mammals, and eventually humans, the horseshoe crab endured. It did not need to reinvent itself because the blueprint it carried was already good enough. There is something deeply humbling about that. We tend to think of evolution as a story of relentless progress, with species constantly improving, becoming more complex, more specialized, more advanced. The horseshoe crab challenges that narrative. It suggests that sometimes the most successful strategy is not to change at all, or at least not much. It reminds us that nature is not striving for novelty or complexity. It is striving for fit, for organisms that mesh perfectly with their environments. And once that fit is achieved, it can last for hundreds of millions of years. The horseshoe crab's persistence also offers lessons for our own species. We are often told that adaptability is key to survival, and that is true. But adaptability is not always about dramatic change. It can also mean the capacity to endure, to withstand upheaval without losing what matters. The horseshoe crab has done exactly that. It has endured everything the planet has thrown at it, not by transforming beyond recognition, but by refining a design that works and holding onto it with tenacity. And yet, despite its resilience, the horseshoe crab now faces challenges unlike any it has encountered before. Habitat loss from coastal development threatens its spawning grounds. Pollution and climate change alter the delicate balance of the environments it depends on. Overharvesting for bait and biomedical use puts additional pressure on populations. These threats are not insurmountable, but they require us to recognize the value of what we stand to lose. Protecting the horseshoe crab is not just about preserving a single species. It is about safeguarding a living link to Earth's ancient past, a creature that has witnessed almost the entire history of complex life and continues to play vital roles in ecosystems and human health alike. As we consider the future of the horseshoe crab, it is worth remembering that its story is far from over. Evolution has carried it through upheavals greater than any we can easily imagine. If given the chance, it will likely continue to scuttle along the world's shorelines long after we are gone. And if that happens, future generations, human or otherwise, may look upon it as we do now, marvelling at a creature that seems to have stepped out of the pages of prehistory into the present. It is one of the quiet ironies of nature that some of the most ancient and enduring creatures are also among the least conspicuous. The horseshoe crab does not roar or charge. It does not dazzle with speed or cunning. It moves slowly, feeds methodically, and spawns under the gentle pull of the moon. And yet it is one of the most successful hunters and survivors the planet has ever produced. It has shaped ecosystems, supported countless species, and even touched human lives in ways few animals have. Its story is not one of dominance or drama, but of quiet persistence, a quality that in the long run may be the most powerful survival strategy of all. From the shadowy depths where nautiluses drift to the sunlit shallows where horseshoe crabs spawn, the ocean is full of such survivors, creatures whose forms have remained stable for hundreds of millions of years because they work. And as we follow their stories deeper into the sea and further into time, we find that each reveals a different aspect of what it means to endure. Some hide behind armor, some lurk in silence, some glide in spirals through the dark. All are living reminders that the past is not gone. It is here, beneath the waves, moving and hunting and waiting. And just beyond the tidal flats where horseshoe crabs scuttle, another of these ancient hunters circles in deeper waters, sleek, powerful, and older than almost anything else still alive. Their story stretches back over 400 million years, and their form has become a symbol of predatory perfection. To understand how ancient hunters still dominate the deep, we must turn now to them. Among the many survivors of Earth's deep past, few command the same mix of fascination and fear as the shark. It is an animal so old that its ancestors were prowling the seas more than 400 million years ago. Long before the first dinosaurs emerged, before trees shaded the land, before the continents themselves had taken the shapes we know today. Through mass extinctions, shifting climates, and changing oceans, sharks have endured, not as static relics but as adaptable, refined predators whose basic design has remained astonishingly stable. They are not just ancient, they are among the most enduring and successful hunters the planet has ever produced, and they continue to dominate the seas much as they did in the Devonian period, when vertebrate life was still young and the future of complex ecosystems was uncertain. To understand the story of sharks is to travel back to a world that would feel alien to us. In the late Silurian and early Devonian periods, about 420 million years ago, life was undergoing profound changes. Plants were beginning to colonize land, building the first terrestrial ecosystems. In the oceans, early fish were experimenting with new forms, developing jaws and fins that allowed them to hunt and maneuver more effectively. Among these pioneering vertebrates were the first sharks, small, slender creatures with cartilaginous skeletons and rows of teeth designed for seizing prey. They bore little resemblance to the powerful hunters we know today, but they carried the seeds of a design that would prove remarkably durable. The earliest sharks, like Cladocelach, were agile swimmers with streamlined bodies and crescent-shaped tails, adaptations that allowed them to pursue fast-moving prey. They lack the heavy, bony skeletons of many other fish, relying instead on cartilage, which is lighter and more flexible. This gave them speed and maneuverability, traits that would become hallmarks of the group. Over time, sharks diversified into an astonishing array of forms, from bottom dwellers that fed on shellfish to swift, open ocean hunters. Some grew massive, like the now extinct megalodon, which reached lengths of over 15 meters and preyed on whales. Others remained small and specialized, occupying narrow ecological niches. But despite this diversity, the fundamental shark blueprint, a cartilaginous skeleton, replaceable teeth, keen senses, and a streamlined body, remained consistent. One of the key features of sharks is their skeleton. Made of cartilage rather than bone, it is both strong and flexible, reducing weight and allowing for greater agility in the water. This is particularly important for predators, as it enables quick bursts of speed and sharp turns during the chase. Cartilage also grows continuously throughout a shark's life, helping repair damage and maintain strength. It is an elegant solution that has served sharks well for hundreds of millions of years, and one that has remained virtually unchanged. Another hallmark of sharks is their teeth, and their approach to replacing them. Sharks are born with multiple rows of teeth that are constantly replaced throughout their lives. As old teeth wear down or break, new ones move forward to take their place, ensuring the shark always has sharp, functional tools for hunting. Some species can lose and replace tens of thousands of teeth over a lifetime. This conveyor belt of weaponry is part of what makes sharks so formidable. It allows them to adapt their feeding strategies to different prey and environments, and it ensures that even older individuals remain effective hunters. But teeth alone do not make a predator. Sharks are equipped with a suite of sensory adaptations that give them an extraordinary awareness of their surroundings. Their sense of smell is legendary. Some species can detect a single drop of blood in an Olympic-sized swimming pool. This sensitivity allows them to locate wounded or stressed prey from great distances. Their hearing is tuned to low-frequency sounds, the kind produced by struggling animals, and can carry over vast distances underwater. Their eyes are adapted for dim light, giving them excellent vision even in the deep or at night, and perhaps most remarkably, they possess specialized organs called the ampullae of Lorenzini, which detect the faint electrical fields generated by the muscles and nerves of other animals. This electroreception allows sharks to find prey even when it is hidden under sand or in murky water. Together, these traits make sharks extraordinarily efficient hunters. They do not need to see their prey to find it, nor do they need to rely solely on speed or brute force. They are guided by a sensory web that extends far beyond our own capabilities, one that lets them read the ocean in ways we can barely imagine. It is a system honed over hundreds of millions of years, tested in every ocean and against every kind of prey. Sharks' reproductive strategies are just as varied and successful as their hunting adaptations. Some species lay eggs encased in protective cases, often called mermaids' purses, which are anchored to seaweed or rocks. Others give birth to live young, either nourishing them internally through a placental connection, or allowing them to feed on unfertilized eggs or smaller siblings within the womb, a strategy known as intrauterine cannibalism. These approaches may seem brutal, but they ensure that the offspring that survive are strong and capable from birth. In the unforgiving environment of the ocean, where predators lurk at every turn. Such head starts can make the difference between life and death. Over their long history, sharks have faced and survived some of the most catastrophic events in Earth's history. They endured the Devonian extinction, which wiped out many early vertebrates. They survived the Permian-Triassic extinction, the most severe mass extinction of all time, which erased over 90% of marine species. They persisted through the asteroid impact that ended the reign of the dinosaurs. Each time, they adapted to new conditions, diversified into new forms, and reclaimed their roles as apex predators. Few lineages in the history of life can match their resilience. This endurance is not the result of luck alone. Sharks' fundamental design is both versatile and robust. Their cartilaginous skeletons allow for a range of body shapes, from the torpedo-like form of the great white to the flattened body of the angel shark, which lies in wait on the seafloor. Their sensory systems give them an edge in environments ranging from shallow reefs to the deep sea. Their reproductive diversity lets them exploit different ecological strategies. In short, they are not specialists locked into a narrow niche. They are generalists with tools that can be adapted to almost any marine environment. That adaptability has been key to their survival. Some species have changed little over vast spans of time. The frilled shark, for instance, retains features reminiscent of its ancient ancestors, including a long eel-like body and rows of needle-sharp teeth. It hunts by lunging forward and swallowing prey whole, a method more common in ancient sharks than in modern ones. Its existence is a reminder that not all sharks have followed the same evolutionary path. Some have remained close to their origins, their forms so well suited to their environments that change was unnecessary. Others, like the hammerhead, have taken evolution in bold new directions, developing wide, flattened heads that enhance sensory perception and maneuverability. Perhaps the most iconic of all modern sharks is the great white, a predator that embodies the efficiency and power of this lineage. Reaching lengths of up to 6 meters and weighing more than 2 tons, it is built for speed, stealth, and strength. Its streamlined body minimizes drag, while powerful muscles propel it in sudden burst capable of launching it clear out of the water in pursuit of prey. Its rows of serrated teeth can saw through flesh and bone, and its sensory suite makes it nearly impossible for prey to hide. Despite its fearsome reputation, the great white is not a mindless killer. It is a careful hunter, often approaching potential prey slowly, assessing it before striking. This caution reflects the reality that large predators cannot afford wasted energy or unnecessary risks. Every hunt must count. The ocean is home to more than 500 species of sharks, each adapted to its own niche. The whale shark, the largest fish on Earth, is a gentle filter feeder that strains plankton from the water. The short-fin mako is one of the fastest fish in the sea, capable of reaching speeds over 70 kilometers per hour. The Greenland shark lives in frigid Arctic waters and may live for more than 400 years, making it the longest-lived vertebrate known. The diversity of forms and lifestyles is staggering, but it all stems from the same ancient blueprint, a design that has been refined but never fundamentally replaced. Sharks' influence on marine ecosystems cannot be overstated. As apex predators, they regulate populations of prey species, maintaining the balance of entire food webs. By preying on the weak, sick, and old, they help ensure the health of fish populations. Their presence influences the behavior and distribution of other species, shaping the structure of marine communities. Remove sharks from an ecosystem, and the effects ripple outward, often in unpredictable ways. Some prey populations may explode, overgrazing vital habitats like seagrass beds or coral reefs. Others may decline as their predators lose control of the food chain. The balance maintained by sharks is the result of hundreds of millions of years of coevolution, and when that balance is disrupted, the consequences can be profound. Despite their resilience and ecological importance, sharks now face threats unlike any they have encountered before. Overfishing driven by demand for shark fins, meat and other products has devastated many populations. Some species have declined by more than 90% in just a few decades. Sharks' slow reproductive rates make them particularly vulnerable to such pressures. Many species take years to reach maturity and produce relatively few offspring. When large numbers are removed from the population, recovery can be slow or impossible. Habitat loss, climate change, and pollution add further challenges, altering the environment sharks depend on and disrupting the food webs they anchor. These modern pressures stand in stark contrast to the natural challenges sharks have overcome. They survived mass extinctions and shifting oceans, but human activity poses a different kind of threat, one that is rapid, global, and relentless. Conservation efforts are underway, from fishing regulations and protected marine areas to bans on finning and trade restrictions. But their success depends on recognizing sharks not as villains, but as vital components of the ocean's living systems, as creatures whose presence is essential to the health of the seas. The story of sharks also carries deeper lessons about evolution and survival. Their endurance is not the result of a single trait or adaptation, but of a combination of features that together create an extraordinarily resilient organism. Their streamlined bodies and powerful muscles make them efficient swimmers. Their sensory systems allow them to hunt in darkness, murk, and vastness. Their reproductive strategies ensure the survival of their young in a hostile environment, and their ecological roles tie them to the very structure of marine life. It is this integration of traits, this evolutionary synergy, that has allowed sharks to persist for so long and remain dominant. Their story also challenges our ideas about what it means to be ancient. Sharks are not unchanged relics from a distant past. They are dynamic, evolving lineages that continue to adapt and diversify. The shark that swims today is not identical to the one that hunted 400 million years ago. It carries the legacy of that ancestor, but it is also the product of millions of years of refinement. Evolution is not a static process, but a constant dialogue between organism and environment, and sharks are among its most eloquent participants. There is something almost paradoxical about their nature. They are both ancient and modern, both deeply rooted in the past and perfectly suited to the present. They are reminders that evolution is not a race toward complexity or intelligence, but a search for solutions that work. And when a solution is found, it can endure for hundreds of millions of years, weathering catastrophes and adapting to new challenges without losing its essence. Sharks also reveal something profound about the nature of power in the natural world. Power is not just about size or strength, it is about efficiency, balance, and integration. The shark's power lies not only in its muscles or teeth, but in the harmony of its design. A design that allows it to glide through the water with minimal effort, sense its prey from afar and strike with precision. It is power without waste, honed by time and necessity. And that kind of power is among the most enduring forces in nature. For humans, sharks are often symbols of fear, their silhouettes conjuring images of danger and predation. But to view them only through that lens is to miss their deeper significance. They are among the oldest living vertebrates on Earth, witnesses to nearly the entire history of complex life. They are architects of marine ecosystems, shaping the world beneath the waves in ways we are only beginning to understand. And they are survivors of unimaginable upheavals, testaments to the resilience and creativity of evolution. When we watch a shark glide through the water, we are seeing more than just an animal. We are watching the result of 400 million years of refinement. We are witnessing a design that has been tested against every challenge the ocean could offer and has emerged stronger each time. We are looking at a predator that has not just survived the passage of time but has shaped it, influencing the course of evolution for countless other species. And we are glimpsing the power of natural selection to create forms that endure not just for millennia, but for epochs. Their story is far from over. Sharks continue to evolve, to adapt, to find new ways to survive in changing seas. They will face challenges we cannot yet foresee, just as they have faced and overcome so many before. And if their past is any guide, they will continue to patrol the oceans long after we are gone, silent and unstoppable, as they have since long before we arrived. From the armoured patience of the horseshoe crab to the spiralling drift of the nautilus, from the quiet endurance of ancient cephalopods to the relentless precision of sharks, the ocean's ancient hunters reveal many faces of survival. Yet there are still others whose stories stretch across unimaginable spans of time, whose presence today seems almost miraculous. One of them is a creature that science once declared extinct, a ghost from the deep past that reappeared to remind us how much we still do not know. And its tale takes us further into the mystery of life's endurance. For most of the 20th century, the coelacanth was a ghost. Its bones, fossilised in ancient rock, were all that remained of a lineage that had once thrived in the seas hundreds of millions of years ago. Paleontologists knew it well as a marker of a vanished era, a strange lobe-finned fish that had played a pivotal role in the evolutionary story of vertebrates, but had vanished from the fossil record around 66 million years ago. Its disappearance coincided with the mass extinction that wiped out the dinosaurs, and for decades scientists assumed it had shared their fate. The coelacanth, they believed, was gone forever, a relic of the Paleozoic and Mesozoic eras, known only from stone and memory. And then, in December of 1938, a fisherman off the coast of South Africa pulled up a net and changed everything. What he caught looked like nothing any modern ichthyologist had seen. It was large, about 5 feet long, with thick lobed fins that looked more like limbs than the fins of any living fish. Its scales were heavy and armoured, its body deep blue and speckled with white. Most striking of all were its paired pectoral and pelvic fins, which moved in an alternating pattern eerily similar to the gait of a walking animal. When scientists examined it, they realised what they were looking at. Against all expectations, a lineage thought to have vanished tens of millions of years ago was alive. The coelacanth, once believed to be a fossil, was a living, breathing creature, a survivor from a world that had ceased to exist. The rediscovery of the coelacanth was one of the most extraordinary moments in modern biology, not only because it revealed the persistence of an ancient lineage, but because it fundamentally changed how scientists thought about extinction and survival. Here was a creature that had remained hidden from science for over 60 million years, living quietly in deep, dark waters while humans built civilizations and rewrote the planet. It was a humbling reminder that the fossil record, for all its power, is incomplete, that the absence of evidence is not always evidence of absence, and that the deep ocean may still harbour forms of life that we assume are long gone. To understand why the coelacanth's survival is so remarkable, we need to step back and look at its lineage. Coelacanths belong to a group of lobe-finned fish called Sarcopterygii, which also includes lungfish and the ancestors of all land vertebrates. In the Devonian period, roughly 400 million years ago, lobe-finned fish were among the dominant vertebrates in the oceans. Their fins, supported by sturdy bones and muscles, were a revolutionary adaptation. Unlike the flimsy, ray-supported fins of most fish, lobe fins could bear weight and move in complex ways. This made them more versatile in shallow water and allowed some species to push themselves along the seafloor or even haul themselves onto land. From these early experiments in mobility would eventually arise amphibians, reptiles, birds and mammals, including us. Coelacanths were part of this evolutionary drama, thriving in the Devonian and Carboniferous seas. They were powerful swimmers and opportunistic hunters, feeding on fish, cephalopods, and other marine animals. Their lobed fins gave them exceptional maneuverability, allowing them to hover and pivot with precision as they stalked prey. Their bodies were built for life in complex environments like reefs and coastal shallows, where agility and control were crucial. Over time, their diversity waned, and by the end of the Cretaceous period, they disappeared from the fossil record entirely. For more than half a century, scientists assumed that was the end of their story. But the coelacanth story did not end. It simply moved out of view. The living species discovered in 1938, later named Latimeria chalumnae, lives not in shallow coastal waters but in deep submarine caves along the coasts of the Western Indian Ocean. There, between 150 and 700 meters below the surface, it hunts in near-total darkness. Its body, once adapted for shallow water maneuvering, is now perfectly suited to this new environment. Its lobed fins allow it to hover motionless in the water column, conserving energy in the nutrient-poor depths. Its powerful tail fin provides bursts of speed when needed, while its sensitive rostral organ, part of an electrosensory system, helps it detect the faint electrical signals of prey. It is a patient predator, spending much of its time drifting slowly, conserving energy, and striking only when an opportunity presents itself. The coelacanth's anatomy is as unusual as its history. Its most distinctive feature, the lobed fins, are supported by bones arranged in a pattern similar to the limbs of tetrapods, the four-limbed vertebrates that would later dominate land. This similarity is no coincidence. It reflects a shared ancestry and offers a living window into the transition from water to land. Studying coelacanth fins has helped scientists understand how the limbs of early amphibians evolved from the fins of their fish ancestors, illuminating one of the most important transformations in evolutionary history. Another remarkable feature of the coelacanth is its intracranial joint, a hinge in its skull that allows the front and back portions of the head to move independently. This joint, found in no other living vertebrate, may help the coelacanth open its mouth wider and generate more suction when feeding, giving it an edge when ambushing prey. Its scales, too, are distinctive, thick cosmoid plates that offer protection and reduce drag. Even its blood is unusual, with a composition adapted to the low oxygen conditions of deep water. Perhaps most fascinating of all is its mode of reproduction. Coelacanths are ovoviviparous, meaning they give birth to live young that develop inside eggs within the mother's body. Gestation can last more than a year, one of the longest known in any fish. The young emerge fully formed and capable of independent survival, though they grow slowly and take many years to reach maturity. This slow reproductive strategy is part of what makes coelacanth populations vulnerable to disturbance, but it is also part of what has allowed them to persist for so long in stable deep-sea environments. The rediscovery of the coelacanth did not end with the South African specimen in 1938. In 1997, a second species, Latimeria menadoensis, was discovered in Indonesian waters, more than 10,000 kilometers from the first. Its existence confirmed that coelacanths were not a single isolated population, but a wider lineage that had quietly persisted in remote corners of the ocean. Each discovery deepened the mystery. How had these fish, thought extinct for millions of years, remained hidden from science for so long? Part of the answer lies in their habitat. Coelacanths inhabit depths that are difficult and expensive to explore, far beyond the reach of traditional fishing methods. They are relatively rare, slow-moving, and live in areas with little human activity. In short, they're easy to overlook, unless by chance one ends up in a net. The coelacanth's survival challenges many of our assumptions about extinction and persistence. It shows that disappearance from the fossil record does not necessarily mean a lineage is gone. Fossilization is a rare event, dependent on a specific set of conditions. Most organisms decompose without leaving a trace, and entire habitats may be underrepresented or absent from the geological record. Deep-sea environments, in particular, are poorly sampled in the fossil record, which means lineages that retreat there can vanish from our view, even if they persist in reality. The coelacanth is a powerful reminder of this blind spot, a caution against assuming that what we cannot see no longer exists. It also underscores the resilience of life in the face of change. Coelacanths survived the Cretaceous extinction that wiped out the dinosaurs and countless marine species. They adapted from shallow coastal habitats to deep-sea refuges. They maintained their distinctive body plan while fine-tuning their physiology for new conditions. Their persistence shows that evolution is not always about radical transformation. Sometimes it's about flexibility within a framework, about making just enough adjustments to endure. Despite their resilience, coelacanths are vulnerable in the modern world. Their slow reproductive rate, low population density, and limited distribution make them susceptible to overfishing and habitat disturbance. Deep-sea trawling, which can destroy their rocky habitats, poses a significant threat. Even incidental capture in fishing nets can have outsized impacts on populations that grow and recover so slowly. Conservation efforts are underway, with protections in place in several countries, but much about their biology and population dynamics remains unknown. Because they live in remote and inaccessible habitats, studying them is challenging, and estimates of their numbers are uncertain. The coelacanth story resonates far beyond marine biology. It touches on fundamental questions about how life persists, adapts, and hides. It reminds us that our knowledge of the natural world is still incomplete, that vast regions of the deep ocean remain unexplored, and that life may still hold surprises as dramatic as the coelacanth's reappearance. It also deepens our understanding of our own evolutionary story. The lobed fins of the coelacanth connect directly to the limbs that allowed our ancestors to walk on land. Its lineage is part of the same tree that gave rise to mammals, birds, and humans. In studying it, we are not just learning about a fish, we are glimpsing a chapter of our own past. There is a certain irony in the coelacanth's status as a living fossil. The term suggests stasis, but the coelacanth is not unchanged. It has continued to evolve, albeit slowly, adapting to new habitats and refining its physiology. What has remained stable is not its genes or every detail of its anatomy, but its fundamental design, a design that works as well today as it did in the Devonian seas. This stability is not a sign of evolutionary failure, but of extraordinary success. It means that the coelacanth found a solution to survival so effective that it has needed little revision. In many ways, the coelacanth is a living embodiment of one of evolution's central truths, that success is measured not by how much a species changes, but by how well it endures. It is easy to be dazzled by rapid evolution, by species that diversify quickly or adapt to new environments in dramatic ways. But there is another kind of evolutionary triumph, the kind that lies in persistence, in finding a form that works and holding on to it. The coelacanth is a master of that strategy. It is not a story of innovation but of endurance, not a tale of rapid change but of patient survival. Its rediscovery also invites us to consider what else might be hiding in the deep. If a lineage thought extinct for 66 million years can persist unseen, what other surprises might await us in the vastness of the ocean? The deep sea covers more than 60% of the Earth's surface and remains one of the least explored regions on the planet. New species are discovered there regularly, many of them unlike anything we have seen before. The coelacanth is a reminder that the deep is not a static graveyard, but a living, dynamic realm full of mysteries. It suggests that our picture of life's history may still have blank spaces waiting to be filled. The coelacanth's existence is also a story about perspective. To us, its survival seems miraculous, a defiance of extinction itself. But from the coelacanth's point of view, there was no disappearance, no dramatic return. Its ancestors simply adapted, moved into new habitats, and continued living as they always had. The drama is ours, not theirs, and that perspective is humbling. It reminds us that the history of life is not centered on us, that the stories we tell about extinction and survival are human constructs layered over a natural world that moves at its own pace, indifferent to our narratives. When we look at a coelacanth today, drifting in the dim blue of a submarine cave, its fins slowly sculling the water, its ancient eyes scanning for prey, we are not just seeing a fish. We are looking at a lineage that has watched continents form and break apart, that has seen ice ages come and go, that has outlived entire dynasties of species. We are looking at a body plan so successful it has endured almost unchanged since before vertebrates walked on land. and we are looking at a survivor that reminds us how much of life's story remains hidden, even now. Its continued existence deepens our appreciation for the complexity of evolution. It shows us that change and stability are not opposites but partners. It teaches us that survival is not always about being the fastest, the smartest, or the most numerous. Sometimes it is about being just right enough to endure, right enough to persist quietly in the margins, right enough to thrive in places where few others can. That lesson, embodied in the slow, deliberate movements of the coelacanth, is one that resonates far beyond the deep sea. From the armoured stillness of the horseshoe crab to the predatory precision of sharks, from the coiled patience of the nautilus to the ghostly persistence of the coelacanth, the ocean is full of creatures that carry the past into the present. Each tells a different story of endurance and adaptation, of how life survives the passage of deep time. And yet, the story is not complete. There are still more ancient hunters whose reign stretches back into prehistory, whose forms have remained stable because they work so well. Some stalk the water's edge, their armoured bodies and patient ambushes unchanged for hundreds of millions of years. Others glide silently through rivers and swamps, embodying a lineage that has weathered every cataclysm Earth could throw at it. Their story awaits us next. Among all the ancient hunters that still roam the earth, few embody the raw, enduring power of evolution as completely as the crocodilians. Their presence is unmistakable. Eyes and nostrils breaking the surface of still water, armoured bodies lying motionless in wait, jaws capable of exerting some of the most powerful bites in the animal kingdom. They are ambush predators of extraordinary patience and efficiency. Apex hunters whose strategies have remained essentially unchanged for tens of millions of years. To see a crocodile lurking in the shallows today is to see not just a living animal, but a direct link to the deep past. A lineage that predates the extinction of the dinosaurs and has persisted through upheavals that reshaped the planet. They are not relics of a bygone world. They are its survivors, still very much at home in the world they helped shape. The story of crocodilians begins deep in the Mesozoic era, over 200 million years ago. At that time, the supercontinent Pangaea was breaking apart, and dinosaurs were just beginning their long reign on land. The ancestors of modern crocodiles, part of a group known as archosaurs, shared a common lineage with dinosaurs and birds. Early crocodilians were far more diverse than their modern descendants. Some were fully terrestrial, sprinting on long legs across floodplains. Others were herbivorous, browsing on plants. Still others were fully marine, equipped with paddle-like limbs for swimming the open seas. These early experiments reflect the evolutionary flexibility of the group, a versatility that would later narrow as the lineage honed in on a particularly successful way of life. By the late Cretaceous period, the familiar crocodilian body plan had emerged. A low, armoured profile, a powerful tail, and a lifestyle centred on water. This design was and remains a masterpiece of evolutionary engineering. The crocodilian's body is built for stealth. Its nostrils, eyes and ears are positioned on the top of its head, allowing it to see, hear and breathe while the rest of its body remains hidden beneath the water's surface. Its skin, thick and covered in bony plates called osteoderms, provides protection and acts as armour against both predators and prey. Its tail, muscular and laterally flattened, propels it silently through the water, ready to surge forward in an instant. But perhaps the most iconic feature of crocodilians is their jaws. Armed with conical teeth and powered by immense jaw muscles, they can clamp shut with astonishing force. The bite of a large saltwater crocodile, for example, has been measured at over 3,700 pounds per square inch, among the most powerful of any animal alive. Once a crocodile seizes its prey, escape is almost impossible. It often employs a brutal technique known as the death roll, spinning its body rapidly to tear flesh from bone or dismember larger prey. Yet for all their power, crocodilian jaws are not designed for chewing. They swallow chunks of food whole, relying on strong stomach acids to break it down. The crocodilian hunting strategy is a study in patience and precision. Unlike sharks, which may range over vast distances in search of prey, or wolves, which pursue their quarry in packs, crocodiles are ambush predators. They spend much of their time motionless, floating just beneath the surface, or lying in wait along the water's edge. They rely on stealth and surprise, striking with explosive speed when prey ventures too close. Their reflexes are so fast that a large crocodile can launch itself from a standstill to full speed in less than a second, covering several meters in a single lunge. This method is energy efficient and highly effective, allowing crocodiles to capture animals far larger than themselves, including antelope, buffalo, and even, on rare occasions, humans. Crocodilians' sensory systems are finely tuned to this predatory lifestyle. Their eyes are adapted for both day and night vision, equipped with a reflective layer called the tapetum lucidum that enhances their ability to see in low light. This allows them to hunt effectively at night, when many prey animals come to the water to drink. Their skin is lined with tiny sensory pits known as integumentary sense organs, which detect minute vibrations and pressure changes in the water. These sensors are so sensitive that a crocodile can detect the splash of a fish or the footsteps of an animal approaching the shore. Their hearing is acute, capable of picking up sounds both in air and underwater, and their sense of smell is excellent, helping them locate carrion or potential prey. One of the most remarkable aspects of crocodilian biology is their reproductive strategy, which reflects a deep evolutionary heritage. Crocodiles, alligators, and their relatives are among the few reptiles to exhibit complex parental care. Females build nests of vegetation and soil, often near the water's edge, and lay their eggs inside. They guard these nests fiercely against predators and regulate the temperature by adding or removing material. The temperature inside the nest determines the sex of the hatchlings. Warmer nests produce males, cooler nests produce females. This temperature-dependent sex determination ties crocodilian reproduction closely to environmental conditions and can influence population dynamics over time. When the eggs hatch, the mother assists her young, gently carrying them in her mouth to the water and remaining nearby to protect them during their vulnerable early weeks. This level of care is rare among reptiles and is a trait crocodilians share with their distant relatives, the birds. It's a reminder of their shared ancestry and a clue to the evolutionary pathways that led from the age of reptiles to the age of birds and mammals. Crocodilians have not just survived, they have thrived through some of the most dramatic events in Earth's history. They endured the asteroid impact that ended the Cretaceous period and wiped out the non-avian dinosaurs 66 million years ago. They adapted to ice ages, changing sea levels, and shifting climates. Their resilience lies in part in their physiology. Crocodilians are ectothermic, or cold-blooded, meaning their metabolic needs are relatively low compared to warm-blooded animals. They can go weeks or even months without eating, surviving on stored energy when food is scarce. They can slow their heart rates and reduce their oxygen consumption, allowing them to remain submerged for extended periods or endure droughts when water dries up. Their adaptability extends beyond physiology to habitat. Crocodilians are found on every continent except Europe and Antarctica, inhabiting environments ranging from tropical rivers and swamps to brackish estuaries and coastal waters. Some species, like the saltwater crocodile, are capable of long-distance oceanic travel, using ocean currents to colonize new areas. Others, like the dwarf caiman, are specialists in small forest streams. This ecological diversity, coupled with a body plan that has changed little in tens of millions of years, is a testament to the versatility and success of the crocodilian lineage. The fossil record reveals just how deep that lineage runs. Early relatives of modern crocodilians, known as crocodilomorphs, were among the dominant predators of the Mesozoic. Some were fully terrestrial and sprinted on long gracile legs. Others were massive semi-aquatic ambush predators similar to modern species but far larger. Deinosuchus, a giant relative from the late Cretaceous of North America, grew up to 10 meters long and likely preyed on dinosaurs that ventured too close to the water. Sarcosuchus, the so-called super croc of Cretaceous Africa, reached lengths of 12 meters and weighed as much as 8 tons. These ancient giants ruled the waterways of their time much as their smaller descendants do today, using the same basic strategies of stealth, patience, and overwhelming power. The continuity of this body plan is striking. Modern crocodilians differ little from their Cretaceous ancestors in overall form and function. This is not because evolution has stood still, but because the crocodilian design works so well. The combination of a powerful bite, stealthy ambush tactics, armoured skin, and low metabolic demands is a near-perfect solution for life as a large aquatic predator. There has been little selective pressure to change it in any significant way. Like sharks and horseshoe crabs, crocodilians are examples of what evolutionary biologists call stabilizing selection, a process that favours existing adaptations and resists drastic change when those adaptations remain effective. Despite their ancient lineage and formidable adaptations, crocodilians face challenges in the modern world. Habitat loss from agriculture, urban development, and dam construction has reduced the wetlands and river systems they depend on. Hunting for their skins and meat, once widespread, drove many species to the brink of extinction in the 20th century. Conservation efforts, including legal protections, captive breeding, and habitat restoration, have helped many populations recover, but others remain vulnerable. Climate change poses new threats, altering rainfall patterns, river flows, and nesting temperatures. Because temperature determines the sex of crocodilian hatchlings, even small shifts can skew sex ratios and affect population viability over time. Their ecological roles make their protection all the more important. As apex predators, crocodilians regulate populations of fish, birds, and mammals, preventing overpopulation and maintaining the balance of aquatic ecosystems. Their nests create microhabitats for other species, and their presence influences the behaviour of prey animals, shaping the structure of food webs. The loss of crocodilians can trigger cascading effects, altering entire ecosystems in ways that are often difficult to predict or reverse. Crocodilians also play an important role in human culture and history. They appear in mythologies and religions from ancient Egypt to indigenous Australia, often as symbols of power, danger, or transformation. They have been both feared and revered, hunted and protected. Their ambush tactics and armoured bodies have inspired legends and cautionary tales, and their resilience has made them enduring metaphors for survival, adaptability, and the relentless passage of time. The relationship between crocodilians and humans is complex. In some regions, they are dangerous predators that occasionally attack people or livestock. In others, they are keystone species whose presence supports entire ecosystems. Conservation efforts often have to balance these realities, finding ways to protect crocodilians while minimizing conflict with human communities. Education, habitat management, and compensation programs for livestock losses are among the strategies used to achieve this balance. From an evolutionary perspective, crocodilians are a window into a world long past. Their closest relatives are birds, a lineage that diverged from the archosaurs more than 240 million years ago. Studying crocodilian anatomy, physiology, and genetics provides valuable insights into the shared ancestry of these two groups, and into the biology of the extinct dinosaurs they both resemble. Their vocalizations, parental care, and heart structure all offer clues about traits that may have been present in the ancestors of birds and dinosaurs alike. Their story is also a reminder of how evolution can shape similar solutions in different lineages. Crocodilians are not fish, yet their body plan, streamlined, muscular, with a powerful tail, mirrors that of sharks and other aquatic predators. This convergence reflects the constraints and opportunities of life in water. Just as sharks refined their design over hundreds of millions of years, so too did crocodilians refine theirs, arriving at a form that has endured with only minor modifications. The similarity is not the result of shared ancestry, but of shared challenges, and of evolution's capacity to solve those challenges in remarkably consistent ways. When we watch a crocodile glide silently through a river, eyes barely breaking the surface, we are witnessing a hunting strategy that has been refined over more than 80 million years. When it explodes from the water in a burst of power to seize its prey, we are seeing a behaviour that has served its ancestors since the age of the dinosaurs. When a female guards her nest and gently carries her hatchlings to the water, we are seeing an instinct that predates mammals and birds. These are not echoes of the past. They are the living present of a lineage that has weathered the deepest currents of time. Their endurance is not guaranteed. Like all ancient lineages, crocodilians must now navigate a world shaped by human activity, one that changes faster than most natural processes. Whether they continue to thrive will depend in part on our choices, on how we manage rivers and wetlands, on how we balance development with conservation, on whether we recognise the value of their role in the ecosystems they anchor. If we succeed, crocodilians will likely persist for millions more years, their eyes and jaws and armour unchanged, their patience and power undiminished. From the deep oceans where coelacanths drift to the swamps and rivers where crocodiles lie in wait, ancient hunters remind us that survival is not always about novelty or speed. Sometimes it's about finding a way of life that works and holding on to it through every upheaval. And yet, not all of Earth's most enduring predators are armoured giants or stealthy ambushers. Some are among the simplest creatures on the planet, lacking bones, brains or blood, yet thriving in the oceans for hundreds of millions of years. Their story, too, is one of extraordinary persistence, and it takes us even further back into the history of life. Long before teeth tore into flesh in the depths, before armoured hunters slid silently through swamps, and before fins and jaws evolved to slice through water in pursuit of prey, the oceans were already alive with hunters of a very different kind. They had no bones, no brains, and no blood. They had no eyes to see the world or limbs to grasp their prey. And yet they moved with a quiet, rhythmic grace, capturing and consuming life with an efficiency that has allowed them to persist for more than 500 million years. These are the jellyfish, pulsating drifters that have floated through Earth's oceans for hundreds of millions of years, long before dinosaurs walked the land, before trees shaded the continents, before complex animals colonized terrestrial environments. They are older than sharks, older than crocodiles, older even than many of the body plans that dominate the planet today. And they remain among the ocean's most enduring and successful predators. To understand the significance of jellyfish, it helps to strip away our assumptions about what a predator is. We tend to think of hunters as active, fast, and armed with sharp tools, claws, teeth, talons. Jellyfish are none of these things. They are soft-bodied, gelatinous and passive, drifting wherever the currents take them. They are slow, often barely moving at all, and seem fragile compared to the armoured or muscular predators they share the ocean with. Yet this apparent simplicity is deceptive. Jellyfish are efficient hunters because their strategy does not depend on speed or strength. It depends on abundance, patience, and some of the most effective biological weaponry ever evolved. Jellyfish belong to a group of animals called cnidarians, which also includes corals and sea anemones. They are among the earliest multicellular animals to appear in the fossil record, with some jellyfish-like organisms dating back more than 550 million years to the Ediacaran period. That means jellyfish were already thriving in the oceans tens of millions of years before the Cambrian explosion transformed marine ecosystems with an explosion of new forms. They were among the first animals to develop organised tissues and specialised cells, innovations that would shape the future of life on Earth. And from the start, their basic body plan, a bell-shaped body with trailing tentacles, proved so effective that it has changed little in the hundreds of millions of years since. The jellyfish body is a study in elegant minimalism, composed of more than 90% water, It is supported not by bones or cartilage, but by hydrostatic pressure and a network of protein fibres. Its bell contracts and relaxes rhythmically, propelling the animal forward in slow pulsing motions. This mode of locomotion is energy efficient, requiring far less effort than the constant swimming of many fish. It also allows jellyfish to drift with ocean currents, carrying them vast distances with little expenditure of energy. Many species combine passive drifting with active pulsing, rising and falling through the water column in search of prey. That prey is captured by the jellyfish's most distinctive feature, its tentacles. These long slender structures are lined with specialized sting cells called cnidocytes, each containing a tiny coiled harpoon known as a nematocyst. When triggered by contact or chemical cues, the nematocyst explodes outward with astonishing speed and force, piercing the skin of the prey and injecting venom. Some jellyfish venoms paralyze small fish and plankton almost instantly, while others break down tissues or interfere with nerve function. The tentacles then draw the immobilized prey toward the jellyfish's mouth, located on the underside of the bell, where it is digested and absorbed. It is a simple but devastatingly effective system, one that requires no brain, no conscious decision, just a hair-trigger cellular response refined over hundreds of millions of years. Despite their lack of a centralized brain, jellyfish are far from mindless. They possess a diffuse nerve net that coordinates their movements and responses to stimuli. Some species have clusters of sensory cells called rhopalia, which can detect light, orientation, and even the chemical composition of the water. Certain jellyfish, like the box jellyfish, have surprisingly complex eyes capable of forming images, a remarkable feat for an organism without a brain. These sensory adaptations allow jellyfish to navigate their environments, orient themselves in currents, and optimize their hunting strategies, even without the neural machinery that underlies behavior in more complex animals. Jellyfish also have one of the most unusual life cycles in the animal kingdom, one that contributes to their resilience and success. Most species begin life as tiny, free-swimming larvae that settle onto a hard surface and transform into polyps, small, sessile forms that resemble miniature sea anemones. These polyps can reproduce asexually, budding off new polyps and forming colonies that may persist for years. When conditions are right, the polyps undergo a process called strobilation, releasing tiny disc-like ephrae that grow into adult medusae, the familiar jellyfish form. This two-stage life cycle, alternating between a stationary polyp and a free-swimming medusa, allows jellyfish to exploit a wide range of environments and survive periods of scarcity. Even if adult populations crash, polyps can persist in hiding, waiting for favourable conditions to return before producing a new generation. This ability to rebound from adversity is one reason jellyfish have persisted through so many global changes. They survived the mass extinctions that wiped out most other species. They adapted to fluctuating ocean temperatures, changing salinity, and shifting currents. Their simple body plan and flexible life cycle give them an advantage in environments where more specialized species struggle. They can thrive in low-oxygen dead zones that kill most fish. They can tolerate wide swings in salinity and temperature. They can even bloom in polluted or nutrient-rich waters created by human activity, turning conditions that harm other organisms to their advantage. In recent decades, jellyfish blooms, sudden population explosions, have become increasingly common in some parts of the world, often linked to overfishing, climate change, and coastal development. With fewer predators and competitors, jellyfish can dominate ecosystems, outcompeting fish for plankton and altering food webs. Some blooms are so massive that they clog power plant intakes, damage fishing gear, and disrupt coastal economies. While these events can be problematic for humans, they're also a testament to the jellyfish's resilience and adaptability. In a rapidly changing ocean, the traits that have sustained them for hundreds of millions of years may become even more advantageous. Not all jellyfish are small or harmless. The lion's mane jellyfish, found in cold northern waters, can reach lengths of over 36 meters from the top of its bell to the tips of its tentacles, making it one of the longest animals on Earth. Its tentacles are lined with millions of nematocysts capable of paralyzing prey in an instant. The box jellyfish, native to the Indo-Pacific, is among the most venomous animals known. Its sting can kill a human in minutes, and its behavior is surprisingly complex. It actively swims toward prey and uses its sophisticated eyes to navigate obstacles, a level of sensory control rare among jellyfish. These extremes demonstrate the diversity and adaptability of the group, showing that even a simple body plan can give rise to a wide range of forms and behaviors. Jellyfish play important roles in marine ecosystems, both as predators and as prey. They feed on zooplankton, fish larvae, and small invertebrates, helping regulate populations and influence the structure of food webs. In turn, they are eaten by sea turtles, certain fish, and even other jellyfish. When they die, their decomposing bodies provide nutrients that support deep-sea communities. Their role in nutrient cycling is particularly important in the open ocean, where resources are often scarce. Some species even form symbiotic relationships with fish or crustaceans, providing shelter among their tentacles in exchange for cleaning or protection from parasites. The fossil record of jellyfish is sparse, largely because their soft bodies rarely fossilize, but the few fossils that do exist show that their basic form has remained remarkably consistent over time. Jellyfish-like impressions found in rocks more than 500 million years old are virtually indistinguishable from modern species. This stability speaks to the effectiveness of their design. A body plan that requires no skeleton, no complex organs, and minimal energy investment has allowed jellyfish to endure through every major environmental upheaval in Earth's history. They are, in a very real sense, among nature's most successful experiments. A design so effective it has never needed replacing. Their evolutionary success also challenges some of our assumptions about intelligence and complexity. Jellyfish have no brains, no centralized nervous systems, and no behaviors we would describe as conscious. Yet, they are among the most ancient and widespread predators on Earth. Their simplicity is not a weakness but a strength, allowing them to survive in environments where more complex organisms cannot. It is a reminder that intelligence is just one of many strategies for survival, and not always the most enduring one. Humans have long been fascinated by jellyfish, drawn to their alien beauty and rhythmic movements. Their translucent bodies, glowing in the light, seem almost otherworldly. They appear fragile, ephemeral, even ghost-like, and yet they have persisted far longer than most of the creatures we think of as powerful. They have watched entire dynasties of species rise and fall, entire ecosystems appear and vanish. Their presence is a reminder that survival is not always about dominance or strength. Sometimes it is about endurance, simplicity, and the ability to thrive where others falter. Jellyfish are also proving valuable to science in unexpected ways. The discovery of green fluorescent protein, GFP, in the jellyfish Equirria victoria revolutionized molecular biology, providing a tool for tracking gene expression, visualizing cellular processes, and studying disease. GFP and its derivatives are now used in laboratories around the world, transforming fields from neuroscience to cancer research. Once again, a creature that predates dinosaurs and mammals by hundreds of millions of years is shaping the cutting edge of human knowledge. Their longevity also offers insights into the nature of aging and regeneration. Some jellyfish species exhibit remarkable regenerative abilities, healing wounds and regrowing lost tissues with ease. One species, Turritopsis dorni, is even capable of reverting its adult medusa form back into a polyp, essentially resetting its life cycle and achieving a kind of biological immortality. While not truly immortal, they can still die from disease, predation, or environmental stress. Their ability to reverse aging is unique among animals and offers tantalizing clues about the mechanisms of cellular regeneration. For all their strangeness, jellyfish are deeply woven into the fabric of life on Earth. They were among the first predators to evolve, shaping the early marine ecosystems that would give rise to more complex forms. They continue to influence oceanic food webs today, both as consumers and as prey. Their life cycles tie them to the rhythms of the sea, from the rise and fall of tides to the seasonal pulses of plankton blooms. They are in many ways the heartbeat of the ocean, ancient, constant and enduring, and yet their story is far from complete. As climate change warms the oceans and human activity alters marine ecosystems, jellyfish are likely to become even more prominent. Their tolerance for low oxygen and variable conditions gives them an edge in environments degraded by pollution and overfishing. Some scientists predict that jellyfish-dominated ecosystems could become more common in the future, reshaping the structure of marine life. If that happens, it will not be the emergence of something new, but the resurgence of something ancient, a return to a world where simple, pulsating hunters ruled the seas. Their persistence also serves as a reminder of how much we still do not know about the ocean. Jellyfish inhabit every part of it, from surface waters to the deepest trenches, yet their diversity, behaviour and ecological roles are still poorly understood. New species are discovered regularly, some in places humans have never explored before. Their movements shape global carbon cycles, their blooms influence fisheries and nutrient flows, and their stings affect ecosystems in ways we're only beginning to grasp. For all their simplicity, jellyfish remain among the ocean's most enigmatic inhabitants. When we watch a jellyfish drifting in the current, its bell pulsing gently, its tentacles trailing behind, we are witnessing a living connection to the dawn of animal life. We are seeing a predator that has survived every catastrophe Earth has faced, that has thrived in conditions that would kill most other creatures, that has endured for hundreds of millions of years without ever needing to become anything more than what it is. Its simplicity is deceptive. Beneath that gelatinous form lies one of evolution's most enduring solutions, a way of life so effective it has outlasted almost everything else. From the patient ambush of crocodiles to the relentless precision of sharks, from the ancient persistence of coelacanths to the drifting lethality of jellyfish, the ocean's hunters show us that there is no single path to survival. Some rely on armour, others on speed. Some depend on intelligence, others on simplicity. All are shaped by the same evolutionary forces sculpted by time and pressure into forms that endure. And yet, among these hunters, there is a group that has taken a different path altogether, one that combines ancient lineage with surprising intelligence, that has abandoned the safety of a shell to embrace adaptability and change. Their story takes us deeper into the evolution of predation and reveals how cunning can become as powerful a weapon as teeth or venom. Among the many ancient hunters that still rule the oceans, few have changed as dramatically or with such astonishing success as the cephalopods. They are a lineage that began its story alongside some of the oldest marine predators on Earth and yet reinvented itself again and again, evolving new forms and new strategies while holding fast to the predatory essence that defined it from the start. They are the heirs of an ancient hunting tradition, descended from creatures that swam the seas more than 500 million years ago, and while their relatives, the nautiluses, chose the path of stability and patience, encasing themselves in protective shells and moving with slow precision, these cephalopods abandoned that armour long ago and embraced a future defined by speed, intelligence, and adaptability. Today, they are among the most remarkable hunters the planet has ever produced, masters of stealth and deception, whose tools are not teeth or claws, but minds and muscles as fluid and versatile as the seas they inhabit. The story of cephalopods begins more than 500 million years ago in the early Paleozoic era. Their ancestors were among the first large active predators to evolve in the oceans, taking advantage of innovations like jet propulsion and buoyancy control to pursue prey in ways no other animals could. Early cephalopods like Orthoceras were long, straight-shelled hunters that prowled the ancient seas during the Ordovician period, using jet propulsion to move and grasping tentacles to seize prey. These creatures were formidable for their time, apex predators in ecosystems still dominated by trilobites and primitive fish. Over time, some cephalopods coiled their shells into spirals, as in the ancestors of the modern nautilus, while others abandoned external shells altogether. It was this latter group, the coleoids, including squids, octopuses, and cuttlefish, that would go on to redefine what a marine predator could be. Losing the shell was a gamble, one that came with risks and rewards. Without the heavy external armour, coleoids became more vulnerable to predation, but they also became faster, more agile, and more flexible. Freed from the constraints of a rigid shell, their bodies could change shape, squeeze through narrow crevices, and dart through the water with astonishing speed. This new mobility opened up ecological niches that had previously been inaccessible, allowing them to exploit a wider range of prey and habitats. It also set the stage for another evolutionary leap, the development of complex nervous systems and sophisticated behaviours. Cephalopods are unique among invertebrates in the complexity of their brains. In fact, their nervous systems rival those of many vertebrates, and their intelligence is among the highest found anywhere in the animal kingdom. An octopus, for example, has more neurons in its arms than most fish have in their entire bodies. Those arms can operate semi-independently, exploring, grasping, and manipulating objects, while the central brain processes information and makes decisions. Squids and cuttlefish, too, display remarkable cognitive abilities, from problem-solving and learning to communication, and even tool use. These are not mindless hunters driven solely by instinct. They are thinkers, capable of adapting their strategies to the circumstances they encounter. Their hunting techniques are as varied and sophisticated as their anatomy. Squids are fast, active predators, using powerful jet propulsion to chase down fish and crustaceans. Their streamlined bodies, fins and siphons make them some of the most agile swimmers in the ocean. Once they are close enough, they shoot out two long feeding tentacles tipped with suction cups or hooks, seizing their prey and drawing it toward their sharp, parrot-like beaks. The attack is swift and precise, over in moments. Some squid species hunt in coordinated groups, surrounding schools of fish and driving them into tight clusters before launching synchronized strikes, a level of cooperative behavior rare among invertebrates. Octopuses, by contrast, are stealth specialists. They rely on patience, cunning, and deception. Many species spend much of their time hiding in dens or blending into their surroundings, waiting for the right moment to strike. Their camouflage abilities are unmatched in the animal kingdom. Specialized skin cells called chromatophores, iridophores, and leucophores allow them to change color, texture, and even reflectivity in fractions of a second. With these tools, an octopus can vanish into a coral reef, mimic the shifting patterns of sand, or transform its appearance to resemble other animals. When prey approaches, the octopus explodes into action, wrapping its muscular arms around the victim and delivering a paralyzing bite with its beak. Some species even use venom to subdue their prey, injecting toxins that immobilize fish, crustaceans, or mollusks before consuming them. Cuttlefish combine aspects of both approaches. They are agile swimmers and adept hunters, using their tentacles to capture prey with speed and precision. But they are also masters of visual communication and deception, using their colour-changing abilities not just for camouflage but for signalling and intimidation. Some species perform hypnotic displays of pulsing light and shifting patterns to confuse or dazzle prey before striking. Others use complex body language to communicate with potential mates or rivals, signalling intentions and status in a visual language we're only beginning to decode. One of the most remarkable aspects of cephalopod intelligence is their capacity for learning and memory. Octopuses in laboratory settings can navigate mazes, open jars, solve puzzles, and even distinguish between different shapes and patterns. They learn from experience, adjusting their strategies based on what works and what doesn't. Some species have been observed using tools, gathering coconut shells or rocks to build shelters, or carrying objects for later use. Others exhibit playful behaviours, interacting with objects in ways that serve no obvious survival purpose. These behaviours hint at a level of cognitive sophistication rare among invertebrates, and suggest that cephalopods experience the world in ways more complex than simple stimulus and response. Their nervous systems are structured very differently from those of vertebrates, yet they achieve similar outcomes. Instead of a centralised brain directing every action, cephalopods distribute much of their neural processing throughout their bodies. Each arm of an octopus, for instance, contains its own network of neurons, capable of independent action and decision-making. This distributed intelligence allows for incredible flexibility and responsiveness, enabling cephalopods to coordinate complex movements and behaviours with speed and precision. It also suggests that intelligence can evolve in radically different ways, shaped by the constraints and opportunities of an organism's body and environment. Cephalopods' evolutionary history is marked by dramatic shifts in form and function. During the Mesozoic era, they shared the oceans with marine reptiles and giant fish, evolving new adaptations to survive in a world full of massive predators. The belemnites, extinct relatives of modern squids, developed internal shells for support and balance. The ammonites, cousins of the nautilus, evolved intricate shell shapes and occupied a wide range of ecological niches before disappearing in the mass extinction that ended the Cretaceous. Through it all, the coleoids, the shellless cephalopods, continued to diversify, refining their strategies and spreading into every marine environment, from shallow coastal waters to the deep sea. Their success is not just a matter of intelligence or agility. Cephalopods are also masters of reproduction and life cycle strategies. Most species grow quickly and reproduce rapidly, producing large numbers of eggs in a short time. Their lives are often brief. Many species live only a year or two, but their fast growth and high reproductive output allow populations to recover quickly from losses. Some species, like the giant Pacific octopus, invest heavily in parental care. Females guard their eggs diligently, cleaning and aerating them until they hatch, often at the cost of their own lives. This level of investment ensures a higher survival rate for offspring and reflects the complex behaviours that have evolved in this lineage. Cephalopods' adaptability extends beyond behaviour and reproduction to their physiology. Their bodies are marvels of soft tissue engineering, capable of squeezing through spaces far smaller than their apparent size. Octopuses can contort themselves into crevices barely larger than their eyes, escaping predators or ambushing prey from unexpected angles. Their arms, equipped with hundreds of suction cups, provide incredible dexterity and strength, capable of exerting precise control over objects and surfaces. Some squids possess photophores, like producing organs that allow them to create bioluminescent displays for communication, camouflage, or luring prey in the deep sea. Others can change the stiffness of their bodies on demand, switching from soft and pliable to firm and resistant as needed. Cephalopods are not without vulnerabilities. Their soft bodies offer little protection against predators, and their short lifespans mean they must reproduce quickly and often. Many are preyed upon by fish, marine mammals, and even other cephalopods. Yet these challenges are also part of what has driven their evolutionary success. Their vulnerability has favoured intelligence, speed, and deception as survival strategies. Their short lives have favoured rapid growth and reproduction, allowing them to respond quickly to environmental changes. And their role as both predator and prey has tied them deeply into the structure of marine ecosystems, influencing the evolution of countless other species. Their ecological importance cannot be overstated. Cephalopods are key predators of fish, crustaceans, and other invertebrates, helping regulate populations and maintain balance in marine food webs. They are also vital prey for larger predators, from sharks and seabirds to whales and seals. Their abundance and rapid turnover make them central to the flow of energy through marine ecosystems. In some regions, their populations fluctuate dramatically, in response to changes in temperature, currents, and prey availability, with cascading effects on the species that depend on them. Cephalopods' relationship with humans is complex and multifaceted. They have been part of our diets for thousands of years, and they play important roles in many cultures, cuisines, and traditions. Their intelligence and problem-solving abilities have made them subjects of scientific fascination, offering insights into the nature of cognition, evolution, and nervous system function. They are also becoming increasingly important as indicators of environmental change. Because they grow quickly and respond rapidly to shifts in ocean conditions, cephalopods can serve as sensitive barometers of ecosystem health. The more we learn about cephalopods, the more they challenge our understanding of life itself. They show us that intelligence is not limited to animals with backbones, that complex behaviours can arise from nervous systems structured very differently from our own. They demonstrate that evolution can take multiple paths to similar solutions, that distributed intelligence can achieve outcomes comparable to those of centralized brains, that soft bodies can be as effective as armored ones, that deception can be as deadly as brute force. They remind us that the story of life is not a linear progression toward a single goal, but a branching tree of possibilities, each shaped by its own constraints and opportunities. Their story also highlights the dynamic nature of evolution. Cephalopods are not living fossils like nautiluses or coelacanths. They are innovators, constantly changing and adapting, pushing the boundaries of what is possible for an invertebrate. Yet they are also deeply ancient, their lineage stretching back to the dawn of complex animal life. This combination of ancient roots and modern innovation makes them unique among the ocean's hunters, creatures that are both a link to the deep past and a glimpse of evolutionary futures. When we watch a squid dart through the water, its body flashing with colour as it propels itself with jets of water, we are seeing the product of more than 500 million years of evolution. When we see an octopus melt into its surroundings, vanishing in plain sight before striking with lightning speed, we are witnessing a hunting strategy honed over eons. When we observe cuttlefish communicating in silent patterns of light and colour, we're glimpsing a form of intelligence that evolved along a path entirely different from our own. These are not just animals. They are the living embodiment of evolution's creativity, the heirs of an ancient legacy reshaped into new and astonishing forms. And their story is still being written. Cephalopods are thriving in a changing ocean, with some populations even expanding as conditions shift. Their rapid growth, flexible behaviours, and adaptable physiology give them an edge in an era of climate change and human impact. They are likely to remain key players in marine ecosystems for millions of years to come, continuing to evolve and diversify in ways we can only imagine. From the drifting simplicity of jellyfish to the cunning intelligence of cephalopods, the ocean's predators show us the many paths life can take to achieve the same goal. Some endure by changing little, others by changing constantly. Some rely on brute force, others on stealth and deception. All are shaped by the relentless pressures of survival, their forms and behaviours sculpted by time into tools that work. And yet, among these ancient hunters, there are still others whose strategies lie not in speed or intelligence, but in patience and endurance. Creatures that travel vast distances and live for centuries, carrying the lessons of deep time in their very bones. Their story takes us into another chapter of life's persistence beneath the waves. Among the ancient hunters that have endured across deep time, few embody the concept of persistence as completely as turtles. They are creatures whose very shape speaks of age, of patience, of an evolutionary path chosen long ago and followed with unwavering success. With their armoured shells, slow movements, and deliberate ways, they seem at first glance to belong to another era, relics from a world long gone. And in many ways they are. Their lineage stretches back over 220 million years into the late Triassic period, when dinosaurs were still newcomers and mammals were tiny nocturnal creatures hiding in the shadows. They have survived asteroid impacts, ice ages, and shifting continents. they have witnessed entire dynasties of reptiles rise and fall, and through it all, they have remained, changed in form and size, but never in essence, patient travellers on a voyage that spans geological epochs. The origins of turtles are still a subject of scientific debate, but their fossil record tells us that their ancestors diverged from other reptiles more than 240 million years ago. Some of the earliest known turtles, like Odontochelys, already bore many of the features that define the group today. A broad, flattened body, a protective shell formed from fused ribs and vertebrae, and a lifestyle adapted to both land and water. Others, like Proganochelys, which lived around 210 million years ago, had a fully developed shell but still retained teeth and some primitive traits. These early forms show that the turtle body plan, one of the most distinctive in the animal kingdom, was established remarkably early and has remained remarkably stable ever since. The turtle shell is one of evolution's most extraordinary innovations. Unlike the exoskeletons of insects or the armor plates of armadillos, a turtle's shell is an integral part of its skeleton. The top, or carapace, is formed from fused ribs, vertebrae and dermal bone, while the bottom, or plastron, develops from the bones of the shoulder girdle and sternum. This structure provides exceptional protection from predators, but it also imposes constraints. Turtles cannot expand their chests to breathe as mammals and most reptiles do, so they have evolved specialized muscles and movements of the limbs and internal organs to draw air into their lungs. These adaptations are a testament to the trade-offs evolution often demands. In exchange for protection, turtles accepted a more complex solution to respiration, a price that has paid off for more than 200 million years. From the start, turtles explored a range of ecological niches. Some remained terrestrial, feeding on plants or small animals and laying their eggs on land. Others returned to the water, where buoyancy reduced the weight of their shells and allowed them to exploit new food sources. Among these aquatic pioneers were the ancestors of modern sea turtles, which would go on to become some of the most remarkable navigators and travellers in the animal kingdom. Over millions of years they evolved streamlined bodies, powerful flippers, and physiological adaptations that allow them to thrive in marine environments, migrating thousands of kilometres across open ocean and diving to depths of more than 1,000 metres in search of food. Sea turtles are among the ocean's most accomplished voyagers. Some species undertake migrations that span entire ocean basins, travelling from feeding grounds to nesting beaches separated by thousands of kilometres. The leatherback turtle, the largest living species, can weigh more than 600 kilograms and migrate over 16,000 kilometres in a single year. Its journeys take it from tropical nesting beaches to the frigid waters of the North Atlantic and Pacific, where it feeds on jellyfish and other soft-bodied prey. To accomplish these feats, sea turtles rely on a suite of navigational abilities that scientists are still working to understand. They appear to use a combination of magnetic cues, wave patterns, and chemical signals to orient themselves and return to the beaches where they hatched, sometimes after decades at sea. This ability to find the same patch of sand across vast distances and after a lifetime of wandering is one of nature's most extraordinary navigational achievements. The turtle's slow and steady lifestyle is often misinterpreted as a sign of fragility or passivity, but it is in fact a winning evolutionary strategy. Turtles are ectothermic, or cold-blooded, which means their metabolic rates are low compared to warm-blooded animals. They require less food to survive and can endure long periods without eating. Some species can go months without food or water, slowing their metabolism to a near standstill. This ability allows them to weather periods of scarcity that would doom many other animals. It also contributes to their exceptional longevity. Many turtles live for decades, and some species can exceed a century. The Galapagos tortoise, though not a hunter, is a close relative and can live well over 150 years. Sea turtles, too, are long-lived, often taking 20 to 50 years to reach sexual maturity, but continuing to reproduce for decades thereafter. Their longevity and slow growth rates are double-edged swords. On one hand, they allow turtles to persist in stable environments for long periods. On the other, they make them vulnerable to rapid changes in human pressures. Because turtles take so long to mature and produce relatively few offspring, populations can take decades to recover from declines. This vulnerability is evident today, as many turtle species face threats from habitat loss, pollution, climate change, and exploitation. Sea turtles are particularly at risk. Their nesting beaches are disappearing under rising seas and coastal development. Their eggs and meat are harvested in some regions, and they are often caught accidentally in fishing gear. Plastic pollution too poses a deadly hazard, as turtles mistake floating debris for jellyfish or other prey. Despite these challenges, turtles remain vital components of marine ecosystems. Sea turtles, for example, play crucial roles in maintaining the health of seagrass beds and coral reefs. By grazing on seagrass, they keep it short and healthy, promoting nutrient cycling and providing habitat for countless other species. Green turtles, which shift from carnivorous diets as juveniles to herbivory as adults, are particularly important in this role. Hawksbill turtles, meanwhile, feed on sponges, preventing them from outcompeting corals and thus helping to maintain the diversity and structure of coral reef communities. Even their nesting activities contribute to ecosystem health, as nutrients from eggs and hatchlings that do not survive enrich coastal ecosystems and support terrestrial and marine food webs. Turtles' reproductive strategies reflect their ancient lineage and the pressures they have faced over millions of years. Most species lay large clutches of eggs in nests dug into sandy beaches or riverbanks. The temperature of the nest determines the sex of the hatchlings, with warmer temperatures producing females and cooler temperatures producing males. This temperature-dependent sex determination ties reproduction closely to climate and makes turtles particularly sensitive to rising global temperatures. Skewed sex ratios with too many females and too few males could threaten the long-term viability of some populations. Once the eggs hatch, the tiny turtles face a perilous journey to the sea, running a gauntlet of predators that include birds, crabs, and fish. Only a small fraction survive to adulthood, but those that do contribute to the next generation of a lineage that has persisted for hundreds of millions of years. The turtle's place in human culture is as deep and enduring as its presence in nature. Across civilizations and centuries, turtles have been symbols of longevity, stability, and resilience. In some mythologies, they are believed to carry the world on their backs, their slow and steady movements reflecting the rhythms of the cosmos. In others, they represent wisdom, patience, and endurance. Their shells have been used as tools, instruments, and ornaments. Their images appear in art, religion, and literature, often as emblems of persistence and the passage of time. Even in modern science, turtles are central to studies of aging and longevity. Their slow metabolisms and extended lifespans offering insights into the biological processes that govern life and death. From an evolutionary perspective, turtles offer valuable lessons about the balance between change and stability. Their basic body plan has remained largely unchanged for more than 200 million years, yet they have adapted to a vast array of environments and lifestyles. Some are fully terrestrial, others fully aquatic. Some are herbivores, others carnivores. Some migrate across oceans, others remain within a small home range their entire lives. This combination of stability and flexibility is a hallmark of evolutionary success. It shows that once a body plan proves effective, it can serve as a foundation for endless variation without losing its core advantages. The diversity of turtles today reflects this adaptability. There are more than 350 species, ranging from tiny freshwater turtles no larger than a human hand to massive sea turtles weighing hundreds of kilograms. Their habitats span the globe, from tropical coral reefs to temperate rivers and even arid deserts. Some, like the snapping turtle, are formidable predators, capable of seizing fish, birds, and small mammals with their powerful jaws. Others are specialized feeders, consuming sponges, jellyfish, or seagrass. Each represents a different evolutionary experiment built on the same ancient foundation, a different way of solving the challenges of survival while remaining true to a basic design that has stood the test of time. Fossil turtles reveal just how deep that design runs. During the Cretaceous period, giant sea turtles like Archelons swam the oceans, reaching lengths of more than 4 meters and weighing up to 2 tons. These ancient giants fed on mollusks and other marine animals, much as modern sea turtles do, and their size offered protection from predators like mosasaurs and sharks. Their existence shows that turtles were major players in marine ecosystems even during the age of dinosaurs, and their descendants continue to fill similar roles today. The continuity is striking. The same fundamental adaptations that allowed Archelon to thrive in Cretaceous seas still allow leatherback turtles to cross entire oceans today. One of the most remarkable aspects of turtle biology is their ability to survive extreme conditions. Some freshwater species can endure months of winter in frozen ponds by slowing their metabolism and relying on anaerobic respiration, drawing oxygen directly from the water through specialized tissues in their cloaca. Others can survive prolonged drought by burrowing into mud and entering a state of dormancy. These abilities reflect the deep evolutionary pressures turtles have faced and their capacity to endure hardships that would kill most other vertebrates. They are not simply slow-moving relics. They are masters of survival, equipped with physiological tools as remarkable as any claw or fang. Their endurance also highlights the resilience of life itself. Turtles have survived every major extinction event of the past 200 million years, including the catastrophic asteroid impact that ended the Cretaceous. They have persisted through ice ages and greenhouse worlds, through rising and falling seas, through continents drifting apart and colliding. Their survival is not the result of luck, but of adaptability and resilience, of strategies that work across a vast range of conditions. They are living proof that evolution does not always favour the fastest or the fiercest, but often the most patient and persistent. Yet even creatures as ancient and resilient as turtles face an uncertain future. Climate change is altering ocean currents, sea levels, and nesting beach temperatures, all of which affect turtle populations. Plastic pollution clogs their digestive systems and entangles their limbs. Fishing nets kill thousands of turtles each year as bycatch. Habitat loss from coastal development destroys critical nesting sites. These threats are unprecedented in their scale and speed, and they test the limits of even the most enduring survival strategies. Conservation efforts around the world are working to protect turtles through beach preservation, fishing gear modifications, and international agreements, but success will require global commitment and cooperation. Despite these challenges, there is reason for hope. Many turtle populations have shown remarkable capacity for recovery when given the chance. Protected nesting beaches have seen increases in hatchling survival. Changes to fishing practices have reduced bycatch in some regions. Public awareness campaigns have shifted perceptions and reduced demand for turtle products. These successes show that even ancient lineages facing modern threats can rebound if human activity aligns with their needs. When we watch a sea turtle glide effortlessly through the water, its flippers moving with slow, powerful strokes, we are witnessing the culmination of more than 200 million years of evolutionary refinement. When we see hatchlings scrambling toward the surf under the cover of night, driven by instincts shaped by deep time, we are watching a story that began long before humans walked the earth. When we hold a fossilized turtle shell in our hands, we are touching a lineage that has weathered the rise and fall of continents, the birth and death of species, the endless churn of geological ages. These creatures are not simply survivors of the past. They are active participants in the present, shaping ecosystems and connecting us to the deep history of life. From the drifting simplicity of jellyfish to the cunning intelligence of cephalopods, from the armoured patience of crocodilians to the slow endurance of turtles, the ocean's ancient hunters show us that there is no single way to persist across time. Each lineage represents a different answer to the same fundamental question: How do you survive in a world that never stops changing? Some answers rely on strength, others on stealth. Some embrace change, others resist it. And yet, they all share one thing, a connection to the deep past and a role in the present that remains vital. But the story of endurance in the oceans is not only about individuals or species, it is also about the strategies that shape entire lineages, the reasons why some creatures evolve rapidly while others remain almost unchanged. Understanding these patterns takes us deeper into the logic of evolution itself and into the secrets of survival written in the history of life. For all the astonishing diversity of life that has ever existed on Earth, for all the branching forms and strange experiments evolution has produced over hundreds of millions of years, one of the most curious truths about the history of life is how often it stays the same. Evolution is not a straight line of constant innovation, nor is it a relentless race toward complexity or intelligence. It is a process shaped by the pressures of survival and the demands of environment, and sometimes the best way to endure is not to change much at all. Across the long sweep of deep time, countless species have vanished, swept away by shifting climates, catastrophic events, or simple competition. Yet some lineages have remained astonishingly stable, their forms and functions barely altered from those of their distant ancestors. Their secret is not stagnation, but sufficiency. They found solutions that worked, and they worked so well that they did not need to change. This phenomenon, known as evolutionary stasis, is not rare. The fossil record is full of organisms that appear early in Earth's history and persist, with minimal modification, for tens or even hundreds of millions of years. The horseshoe crab is one of the most famous examples. Its basic body plan, a domed carapace, a spiny tail, and 10 jointed legs, has remained virtually unchanged for more than 450 million years. During that time, entire continents have shifted, seas have opened and closed, and lineages have risen and fallen. Yet the horseshoe crab continues to crawl along shallow seabeds and spawn on sandy beaches just as it did before vertebrates even walked on land. Its success is not an accident. It is the result of a body plan so effective and a lifestyle so well suited to its environment that natural selection has had little reason to alter it. The nautilus tells a similar story. Its chambered shell and jet-propelled locomotion have remained largely the same for more than 500 million years. The coelacanth, once thought extinct, still swims with lobed fins much as its ancestors did 400 million years ago. Crocodilians today hunt in ways that would have been familiar to their Cretaceous forebears. Jellyfish drift through the seas using the same pulsing movements their ancestors used before the first vertebrates evolved. These creatures are not frozen in time. They are still evolving, still adapting to the changing conditions around them. But the core elements of their design, the traits that make them successful, have remained stable because they continue to work. Why some lineages change rapidly while others remain relatively constant is one of the central questions of evolutionary biology. The answer lies in the interplay between environment, adaptation, and selective pressure. Evolution is driven by changes in genetic variation that affect survival and reproduction. When an environment is stable and a species' adaptations suit it well, there is little pressure for major change. Small adjustments may occur, refining existing traits or optimizing them for new conditions, but the overall body plan can remain intact for millions of years. This is the essence of stabilizing selection, a form of natural selection that favors the status quo and weeds out deviations that reduce fitness. It is not that evolution stops, rather, it acts to preserve what works. Conversely, when environments change rapidly or dramatically, or when new competitors or predators emerge, selective pressures intensify and lineages may evolve more quickly. This is why periods of environmental upheaval, such as mass extinctions, are often followed by bursts of diversification as species adapt to new conditions and niches. But even in these times, some lineages weather the changes with minimal modification. They may shift their ranges, alter their behaviours, or adjust their physiology without fundamentally altering their forms. Their resilience lies not in their ability to innovate, but in the versatility and robustness of their existing designs. The idea that stability can be a form of success runs counter to many popular conceptions of evolution. We are used to thinking of evolution as a process of progress, of constant improvement and transformation. But evolution has no goal. It does not strive for novelty or complexity. It is a blind process that selects for traits that enhance survival and reproduction in a given context. If a lineage achieves a form that meets those demands effectively, it may remain relatively unchanged for as long as the environment remains stable. Change for its own sake is not favoured. What matters is fitness, the match between organism and environment, and sometimes that match is already near perfect. The concept of evolutionary stasis also reveals something important about the nature of adaptation. Adaptations are not just physical traits like shells, fins, or jaws. They can include behaviours, life histories, and ecological strategies. The crocodilian ambush, the jellyfish's drifting hunt, the horseshoe crab's spawning migrations, these are as much adaptations as any anatomical feature. And because they work, they endure. They persist not because evolution has failed, but because it has succeeded in finding a solution that remains effective even as the world changes around it. The persistence of ancient body plans also reflects the environments these creatures inhabit. Many of the lineages that exhibit long-term stability live in habitats that, while not static, have remained relatively consistent over geological timescales. The deep ocean, for example, is one of the most stable environments on Earth. Its temperatures, pressures, and chemical composition change slowly and predictably compared to surface environments. Creatures like the coelacanth or deep-sea jellyfish inhabit these stable realms, where dramatic shifts in selective pressures are rare. In contrast, lineages that live in rapidly changing environments, such as shallow coastal zones, terrestrial ecosystems, or freshwater rivers, often show more frequent and pronounced evolutionary change. But stability is not just about environment. It is also about ecological role. Many ancient lineages occupy niches that have changed little over time. The horseshoe crab is still a benthic scavenger. The nautilus still hunts small prey in the deep ocean. Crocodiles still lurk at the water's edge, waiting to ambush passing animals. These niches are not static, but they are consistent enough that the strategies and body plans that evolve to exploit them remain effective. The organisms that occupy them are not locked into a rigid past. They are simply well matched to the present, a present that, in some environments, looks much like the distant past. The phenomenon of stasis is not limited to ancient lineages. Even among more recently evolved groups, we see examples of stability when conditions allow. Some species of sharks, for instance, show little difference from their ancestors of 100 million years ago. Certain birds and mammals, too, have remained largely unchanged for millions of years. What unites these examples is not age, but effectiveness. They have found ways of living that require no radical redesign. This does not mean that stasis is without risks. A body plan that works well in one environment can become a liability in another. If conditions change too quickly or too drastically, a lineage that has remained stable may struggle to adapt. Many ancient groups that once flourished have disappeared for precisely this reason. The Ammonites, cousins of the Nautilus, were extraordinarily successful for hundreds of millions of years, but they vanished at the end of the Cretaceous when rapid environmental changes outpaced their ability to adapt. The trilobites, dominant marine arthropods for more than 270 million years, met a similar fate. Stability is a strength, but it can also be a vulnerability when the world changes too much or too fast. Human activity has accelerated such changes in ways that are unprecedented in Earth's history. Climate change, habitat destruction, pollution, and overexploitation are altering ecosystems at a pace that even the most resilient lineages may struggle to match. Many species that once thrived for millions of years are now endangered. Horseshoe crab populations have declined in parts of their range due to habitat loss and overharvesting. Sea turtles face rising temperatures that skew their sex ratios. Coral reefs, home to countless species that have endured for millennia, are bleaching and dying as oceans warm. These pressures test the limits of evolutionary stability and force even ancient survivors into new and uncertain territory. Yet the story of stasis is not one of inevitability. It is a reminder that survival is not about constant change, but about finding solutions that work and holding on to them as long as they do. It is about resilience and persistence, about the power of a good idea to endure across vast spans of time. It shows us that evolution is not a ladder, but a branching tree, with some branches twisting and changing rapidly, while others remain steady and strong. It reminds us that life's history is not a story of progress, but of persistence, of forms and strategies that have stood the test of time. The lesson extends beyond biology. In a world that often prizes novelty and innovation, the success of ancient lineages reminds us of the value of stability and continuity. It shows that survival is not always about being the newest or the most advanced. Sometimes it is about being well suited to the task at hand, about refining what works and resisting unnecessary change. It is about endurance, about weathering the storms of time without losing what makes you successful. The persistence of ancient hunters also reveals the interconnectedness of life. These creatures do not exist in isolation. Their stability shapes the ecosystems around them. The presence of crocodiles influences the behavior of prey animals and the structure of aquatic habitats. The spawning of horseshoe crabs sustains migratory shorebirds that feed on their eggs. The grazing of sea turtles maintains seagrass beds that support countless other species. Stability in one lineage ripples outward, shaping the evolution and ecology of many others. It's a reminder that evolution is not just about individual species, but about the complex webs of interaction that bind life together. Even the concept of what it means to stay the same is more complex than it first appears. No lineage is truly static. Genetic changes continue to accumulate, and subtle shifts in form and function occur over time. What remains constant are the broad outlines, the overall body plans, the fundamental ecological roles, the core strategies. These are the elements that endure because they work, because they solve the challenges of survival in ways that remain effective even as the details change. When we look at a horseshoe crab crawling along the seafloor, we are seeing not a fossil, but a solution, a way of living that has worked for nearly 500 million years. When we watch a nautilus rise and fall in the deep ocean, we are witnessing a design that solved the problem of buoyancy and mobility before most animals had even evolved eyes. When we see a crocodile explode from the water in an ambush, we are watching a strategy that has dominated riverbanks since the time of the dinosaurs. These creatures are not stuck in the past. They are masters of the present, their success written not in the speed of their change but in the depth of their endurance. And in that endurance lies a deeper truth about life itself. Evolution is not just about adaptation to change. It is also about stability in the face of it. It is about the ability to persist, to endure, to hold steady when the world allows it. The history of life is written not only in bursts of innovation, but in long stretches of constancy, in forms that remain because they do not need to be replaced. Those forms remind us that the story of life is not just one of transformation, but of tenacity, not just of novelty, but of persistence. From the patient endurance of turtles to the drifting simplicity of jellyfish, from the ambush strategies of crocodiles to the unchanged bodies of horseshoe crabs, the ocean is full of creatures that have survived not by constantly reinventing themselves, but by staying true to what works. Their persistence is a testament to the power of evolution's quieter forces, the ones that preserve as much as they change. And yet, even as they endure, they continue to shape the world around them, influencing the course of evolution and the structure of ecosystems in ways that ripple through time. They are the steady heartbeat of life's story, the enduring presence that links the distant past to the unfolding present. And as we look deeper into the oceans and back into the fossil record, we begin to see that their story is not just about what has been, but about what still is, and about what will continue to be as life carries forward into the future, from the unchanged forms that have endured for hundreds of millions of years to the predators that have constantly reinvented themselves. The story of the ocean's hunters is one of astonishing diversity and resilience, and as we near the end of this exploration, it is worth returning to where we began, to the idea that these creatures are more than relics of a distant past. They are active participants in the world today, shaping ecosystems, influencing evolution, and reminding us of our own fleeting place in the grand sweep of time. Their presence invites reflection on what it means to endure, to adapt, and to belong to a story far larger and older than ourselves. And that reflection leads naturally to the final part of this journey, a look at the timeless watchers of the deep and what they reveal about the enduring nature of life itself. Across the vastness of Earth's history, through all the upheavals and extinctions and transformations that have reshaped life again and again, the deep ocean has remained a place apart, a realm of constancy and darkness, where time itself seems to stretch and slow. It is a world largely untouched by the rapid changes that sweep across the surface, a place where light never penetrates and pressures rise to crushing extremes. It is also a world where some of the planet's most ancient hunters continue to thrive, creatures that have endured for hundreds of millions of years in silence and shadow, watching the slow unfolding of evolution from a realm few have ever seen. These are the deep's timeless watchers, predators and scavengers alike, whose existence connects the distant past to the present, and whose survival reveals truths about life that extend far beyond the boundaries of the ocean. To step into this world is to enter an environment profoundly different from the one we inhabit. At depths beyond 1,000 meters, sunlight disappears entirely. Temperatures hover just above freezing, and pressures can exceed 1,000 times what we experience at the surface. Food is scarce, delivered only in the form of organic detritus falling from above, a slow rain of dead plankton, fecal pellets, and decaying matter known as marine snow. Yet life persists here in astonishing variety, from microbes to colossal squid, from bioluminescent fish to gelatinous drifters. The organisms that inhabit these depths have evolved strategies as strange as the environment itself, and many of them trace their lineages back hundreds of millions of years. They are not relics of a forgotten past. They are the continuing story of life's endurance in one of its most challenging arenas. Among the most remarkable of these deep-dwelling hunters are the giant squids and colossal squids, elusive cephalopods that inhabit the twilight and midnight zones of the ocean. Known to science primarily from the remains found in the stomachs of sperm whales or washed ashore after storms, these creatures have long occupied a place at the edge of myth. The giant squid, Archaeoteuthis dux, can reach lengths of over 12 meters, its long tentacles armed with powerful suckers that help it seize prey in the darkness. The colossal squid, Mesonychoteuthis hamiltoni, is even larger by mass and wields rotating hooks on its tentacles, adaptations for capturing large, fast-moving prey in the frigid waters of the Southern Ocean. These animals are descendants of ancient cephalopod lineages, refined and specialized for life in the deep. They hunt in a world without light, relying on touch, sensitivity to pressure waves, and perhaps even long-range chemical cues to locate their prey. Their lives unfold in near-total secrecy, but their very existence is a reminder of the vastness and complexity of the deep, and of the predators that have evolved to master it. Sharks, too, are among the deep's most enduring inhabitants. While many species hunt in coastal waters, others descend into the darkness, adapted to the cold and pressure of the deep sea. The Greenland shark, for example, is one of the most remarkable vertebrates on the planet. It lives in the frigid waters of the North Atlantic and Arctic Oceans, and may live for more than 400 years, making it the longest-lived vertebrate known. It moves slowly through the darkness, feeding on fish, seals, and even carrion, its metabolism tuned to the icy environment. Its longevity, slow growth, and reproductive strategy reflect a life lived at the pace of the deep, where resources are scarce and patience is essential. Other deep-sea sharks, like the goblin shark with its protrusible jaws, or the frilled shark with its eel-like body and ancient features, retain traits that link them to ancestors that swam the oceans long before mammals existed. These species remind us that the shark lineage is not just ancient in its origins, but diverse and adaptable enough to colonize even the most extreme habitats. The deep is also home to some of the ocean's most enigmatic scavengers, animals that rely on the death of others for their survival, yet play a crucial role in the ecosystem. Hagfish are among the strangest and oldest of these. Jawless, eel-like, and slime-producing, they belong to a lineage that diverged from other vertebrates more than 500 million years ago. When a whale or large fish falls to the seafloor, hagfish arrive quickly, burrowing into the carcass and consuming it from within. Their slime, produced in vast quantities when threatened, deters predators and can clog the gills of would-be attackers. Their bodies are primitive, lacking jaws and paired fins, yet their strategies are effective and their lineage has persisted for longer than almost any other vertebrate group. Alongside them are deep-sea scavenging sharks and amphipods, which strip carcasses to the bone within days or weeks. These communities recycle nutrients and return them to the ecosystem, sustaining life in a place where resources are otherwise scarce. In the inky darkness, bioluminescence becomes a crucial tool, and one that many ancient hunters have mastered. More than 80% of deep-sea organisms produce their own light, using it for communication, camouflage, and hunting. The anglerfish is one of the most famous examples. Its lineage dates back more than 100 million years, and its predatory strategy is as effective now as it was then. A fleshy lure, tipped with glowing bacteria, dangles from a modified dorsal spine, drawing prey close in the darkness. When an unsuspecting fish approaches the light, the anglerfish snaps its jaws shut in an instant, swallowing the prey whole. This strategy relies on patience and deception rather than speed or strength, a hallmark of life in the deep. Many anglerfish also exhibit extreme sexual dimorphism, with tiny males fusing to the bodies of much larger females, providing sperm in exchange for sustenance, a reproductive adaptation to the challenges of finding a mate in the vastness of the deep sea. Bioluminescence is not limited to predators. It is also used by prey to confuse or evade attackers. Some squid release glowing clouds to distract predators, much like ink. Certain fish use counter-illumination, producing light on their undersides to match the faint glow filtering down from above, rendering them nearly invisible from below. These adaptations are part of an evolutionary arms race that has been unfolding for tens of millions of years, shaping the behaviour and physiology of both hunters and the hunted. They also demonstrate how life in the deep is governed by different rules than life at the surface. Here, light is a weapon, a lure and a shield, and those who wield it well have a decisive advantage. Even among the simplest creatures of the deep, endurance is the rule. Sponges, some of which have persisted with little change for over 600 million years, form the foundation of many deep-sea ecosystems, filtering vast amounts of water and providing habitat for other organisms. Certain species of corals grow into massive reefs on seamounts and continental slopes, their colonies living for thousands of years and supporting complex communities of fish and invertebrates. These structures become hunting grounds for predators and refuges for prey, shaping the flow of energy and nutrients in the deep ocean. Their persistence shows that even in a place where life moves slowly and conditions are extreme, stability and continuity remain powerful strategies. The deep ocean is also a repository of evolutionary experiments that challenge our understanding of life. Some organisms thrive at hydrothermal vents, where superheated, mineral-rich water gushes from the seafloor. These ecosystems, first discovered in 1977, are fueled not by sunlight but by chemosynthesis, the use of chemical energy to support life. Here, giant tube worms, vent crabs, and specialized fish form communities built around microbial life that converts chemicals like hydrogen sulfide into organic matter. Many of these species are ancient in lineage, their ancestors predating the rise of complex ecosystems on land. Their existence reveals that life can thrive in places once thought impossible, and suggests that similar ecosystems could exist on icy moons or other planets beyond Earth. The creatures of the deep also highlight the role of longevity and slow life histories as survival strategies. Many deep-sea fish grow slowly, mature late, and live for decades or even centuries. The orange roughy, for example, can live for more than 200 years, growing slowly in the cold, nutrient-poor waters of the deep. Such strategies make sense in an environment where energy is limited and growth must be balanced against survival. They also make these species vulnerable to overfishing and other human impacts, as their populations recover slowly from depletion. Understanding these life histories is crucial for managing and protecting deep-sea ecosystems, which are increasingly threatened by human activities like deep-sea mining, bottom trawling, and climate-driven changes in ocean circulation. The deep sea remains one of the least explored regions on Earth. Despite covering more than 60% of the planet's surface, it has been mapped in detail in only small patches, and much of its biodiversity remains unknown. New species are discovered with nearly every expedition, from glowing jellyfish and ghostly octopuses to armoured fish and bizarre crustaceans. Many of these discoveries are not new in an evolutionary sense. Their lineages may stretch back tens or hundreds of millions of years, but they are new to science, reminders of how much we still do not know about the planet we call home. The deep holds secrets not just about life today, but about life's past, about how ancient lineages endured and adapted, and about the forms they may still take in places we have yet to explore. The endurance of these deep-sea hunters and scavengers also forces us to rethink our place in the grand story of life. Human civilization is a blink of an eye compared to the span of time these creatures have existed. The Greenland shark swimming beneath Arctic ice today was born before many of our modern nations existed. Hagfish were already ancient when dinosaurs first appeared. Anglerfish have hunted in the dark since mammals were still scurrying beneath the feet of reptiles. These timeframes dwarf our own history and remind us that life's story is far larger and older than we often imagine. The deep ocean, with its timeless watchers, is a living archive of that story, not preserved in stone, but written in flesh and behaviour, in strategies and adaptations that have endured for hundreds of millions of years. Their persistence also offers perspective on the challenges life faces now. The deep ocean is changing as climate change alters temperature gradients, oxygen levels, and circulation patterns. Human activities threaten to disturb ancient ecosystems with consequences we cannot fully predict. Yet the resilience of life in the deep gives reason for hope. These creatures have endured mass extinctions, shifting continents, and dramatic climate shifts. Their survival suggests that life, given the chance, will find ways to persist even in the face of great upheaval. The question is not whether they can endure, but whether we will allow the conditions that make their endurance possible to continue. What unites the deep's timeless watchers is not a single body plan or hunting strategy, but a shared mastery of endurance. Some, like the Greenland shark, achieve it through longevity and slow metabolism. Others, like the anglerfish, rely on patience and deception. Still others, like the giant squid, depend on size and stealth. Their strategies differ, but their outcomes are the same: survival across unimaginable spans of time. They are not relics of the past, but active participants in the present, shaping ecosystems, influencing evolutionary trajectories, and carrying the lessons of deep time into the modern world. When we think of the deep sea, it is easy to imagine it as a distant alien realm, disconnected from our lives. But the truth is that it is intimately connected to the planet as a whole. The deep ocean regulates Earth's climate, storing vast amounts of carbon and distributing heat around the globe. It drives nutrient cycles that sustain life at the surface. It influences weather patterns and supports fisheries that feed billions of people. And the creatures that inhabit it, the sharks and squid, the scavengers and glowing hunters, are integral to these processes. Their presence and persistence help maintain the stability of the systems we depend on, even if we rarely see or think about them. In their endurance, these deep-sea creatures also offer a kind of humility. They remind us that the world is not built for us alone, that it has been shaped by countless forms of life over eons and will continue to be shaped long after we're gone. They show us that power and persistence can take many forms, not just speed or intelligence or strength, but patience, stability, and the quiet mastery of difficult environments. They invite us to see the ocean not as a distant frontier, but as a living archive of Earth's history, a place where the past is still present and where the lessons of survival are written in every drifting jellyfish, every lurking shark, every patient scavenger. As we look deeper into the ocean and deeper into time, we begin to understand that these ancient hunters are not just curiosities or remnants of a vanished world. They are essential threads in the fabric of life, reminders of where we come from and hints of where life may go. They have endured through cataclysm and calm alike, through ice ages and greenhouse worlds, through the rise and fall of continents and species, and they will likely endure long after we are gone, continuing their slow, patient watch over the deep, from the shores where horseshoe crabs spawn under moonlight to the abyssal plains where giant squid drift through darkness, from the coral reefs patrolled by sharks to the frozen waters where Greenland sharks glide unseen. The ancient hunters of the sea tell a story that is both humbling and profound. It is a story of persistence, of strategies that endure, of forms that work. It is a story that reaches back to the dawn of complex life and stretches forward into a future we can scarcely imagine. And it is a story we are part of, whether we realize it or not, because the same forces that shaped them continue to shape us. The deep is not separate from our world. It is our world, as it has always been, vast, ancient, and alive, watched over by creatures that have seen more ages than we can comprehend and will likely see many more,